There is a star so large, so luminous in the deep infrared, and yet so deceptively quiet that it's been hiding in plain sight, tucked away in the southern skies, barely noticed by the average stargazer. It is neither the most famous nor the most glamorous object in our galaxy, yet R Doradus is a silent titan, close, colossal, and undergoing one of the most fascinating phases in stellar evolution. Unlike the dazzling constellations that dominate the night for the casual observer, R Doradus does not dazzle in visible light. It lurks just beyond our immediate perception, a behemoth cloaked in cool crimson, glowing with quiet intensity like a cosmic ember. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Imagine a star so large that, were it to trade places with our Sun, it would engulf the orbits of Mercury, Venus, Earth, and Mars. Now imagine that this massive entity is not light years away in some distant galaxy, but right next door in galactic terms, just about 200 light years away. On a cosmic scale, that's closer than many of the stars you can see with the naked eye. R Doradus isn't just an astronomical curiosity. It's a living relic, a glowing, breathing witness to the ancient forces that govern the life and death of stars. As our understanding of the cosmos expands with more powerful telescopes, it's these quiet giants that whisper the most profound truths about the universe. R Doradus, though nearly invisible to unaided vision, roars in the infrared and carries secrets of stellar evolution, mass loss, future planetary systems, and even our Sun's ultimate destiny. This essay is your voyage into the life of this remarkable red giant, an odyssey through science, mystery, and cosmic legacy. We begin at the outer fringes of Dorado, the constellation where R Doradus dwells. Though the name might not resonate the same way as Orion or Ursa Major, Dorado harbors one of the most important celestial bodies quietly shaping our understanding of how stars live and die. From its enormous size to its pulsating heartbeat, from its elemental breath enriching the galaxy to the legacy it will leave behind, R Doradus is not just a star. It's a story. A story still being written in stardust and light, even now, 200 light-years from Earth. To understand the grandeur of R Doradus, we must first ground ourselves in what it actually is: a red giant star nestled within the southern constellation Dorado. While the name Dorado may not ring a bell for many, especially those in the northern hemisphere, it holds celestial gems like the Large Magellanic Cloud and, more subtly, R Doradus, one of its quietly burning stars. R Doradus, also catalogued as HD 29712, is classified as an M-type red giant, a spectral designation indicating a cool surface temperature, and the signature red hue that defines the aging giants of the universe. At just around 200 light-years away from Earth, R Doradus is remarkably close when placed on the galactic map. For perspective, light from R Doradus began its journey to us not long after Galileo first pointed his telescope at the heavens. Most stars we commonly refer to by name, like Betelgeuse or Antares, are hundreds, if not thousands, of light-years farther. In contrast, R Doradus lies right within what astronomers consider our stellar neighborhood. Yet despite its proximity, R Doradus remains relatively obscure outside of scientific circles. Why? Its position in the southern sky means it's invisible to observers above certain northern latitudes. Even in locations where it can be seen, its visible magnitude hovers between 4.8 and 6.6, often just below the threshold of naked eye visibility in light-polluted environments. It's the kind of star you don't stumble upon, you have to search for it, and when you do, you're rewarded not just with its light, but with insight into stellar evolution. R Doradus is a red giant in the late stages of its stellar life. This means it has exhausted the hydrogen in its core, the fuel that kept it stable for billions of years, and now burns helium and other heavier elements in shells surrounding its increasingly unstable core. The star's envelope has puffed outward, becoming tenuous, extended, and dramatically cooler than it once was. In essence, it's undergoing a dramatic transformation, shedding mass, pulsating with strange rhythms, and preparing for its final act as a white dwarf surrounded by a planetary nebula. Its classification as a red giant situates it among the most well-understood, yet still mystifying, phases of stellar evolution. These stars don't go quietly. They expand, they pulse, and they expel matter at incredible rates, seeding the cosmos with the ingredients for future stars, planets, and perhaps even life. R Doradus, in all its unassuming presence, is actively contributing to that grand cosmic cycle. And it's this very duality, its physical nearness and observational elusiveness, that makes R Doradus so compelling. It's an object that bridges the vastness of stellar processes with the intimacy of our local cosmic environment. It reminds us that monumental cosmic events don't always happen in distant galaxies. Sometimes, they unfold quietly in our own backyard, just a few hundred light-years away. When you look up into the night sky and see a star, even the brightest among them appear as mere pinpricks of light. It's easy to forget that these glowing dots are often monstrously large, some so massive and voluminous that they dwarf our Sun to a point of insignificance. R Doradus is one such star. Its true scale is almost beyond comprehension, over 350 times the diameter of the Sun. That isn't just a number, it's a staggering reality that places this red giant among the largest known stars by apparent size in Earth's sky. To grasp what that means, imagine lifting R Doradus and placing it gently into our own solar system, taking the position of our Sun. If you did this, its outer atmosphere would engulf the orbits of Mercury, Venus, Earth, and even reach beyond Mars. All four inner rocky planets would find themselves within the star's swollen, gassy layers. Earth wouldn't just be orbiting a star, it would be inside it. This isn't just a theoretical comparison. Astronomers have carefully measured R Doradus's angular diameter using a technique called stellar interferometry. What makes it especially noteworthy is that, in terms of angular diameter, how large it appears in the sky, it ranks as the second largest star seen from Earth, second only to the famed Betelgeuse. But while Betelgeuse is around 550 light-years away, R Doradus is only 200. Its closer proximity means that although it's smaller in actual size compared to true supergiants, it appears incredibly large when viewed through high-resolution instruments. Now, being 350 times the diameter of the Sun doesn't mean it's 350 times more massive. That's the paradox of red giants. They are large but diffuse. Their outer envelopes are bloated and tenuous, more like puffs of stellar gas than solid structures. In fact, R Doradus is believed to have a mass only a few times greater than our Sun, and in some estimates, even less than twice as massive. That small core is struggling to hold on to the vast outer layers it has inflated during the late stages of its life. The outer layers of R Doradus are so distended that gravity has only a weak grip on them. That's part of the reason why the star is actively losing mass, shedding its outer atmosphere into space over time. And because of its colossal size, the surface gravity at the edge of R Doradus is extremely low, far weaker than on the Sun, allowing material to escape with relative ease, carried away by stellar winds and radiation pressure. R Doradus's size isn't just a number for trivia, it has profound implications. The huge surface area means that although the star's surface temperature is low, it still emits an enormous amount of energy. A cooler object can shine incredibly brightly, provided it has enough surface to radiate from, and R Doradus certainly does. It also raises fascinating questions about how such massive stars maintain equilibrium. The interior of R Doradus is a balancing act between the outward pressure of nuclear fusion and the inward pull of gravity. But in this late stage, that balance begins to falter. Instability set in, leading to pulsations, giant heaving motions of the entire star's envelope, and ongoing, uneven shedding of mass. The very size of R Doradus ensures that its life is not a quiet one. It swells, pulses, and breathes like a living organism, a process driven by physical forces so immense they stretch the boundaries of comprehension. From our vantage point on Earth, we can't see this mammoth size directly with our eyes. It appears as a small point of light, faint and unremarkable. But behind that pinprick lies a stellar balloon, a star that could swallow our solar system whole. It's a reminder of how deceptive appearances can be, and how much more is going on in the cosmos than meets the eye. One of the most poetic and revealing features of R Doradus is its color. To the naked eye, if conditions are just right, it might appear as a faint reddish glow in the southern sky, but to astronomers using specialized instruments, its deep red hue tells an entire story, a story of age, transformation, and impending stellar death. The red color of R Doradus is not just for show. It's a consequence of the star's low surface temperature, which hovers around 2740 Kelvin. That's significantly cooler than our Sun, whose surface temperature is about 5778 K. When an object emits light due to heat, a phenomenon known as blackbody radiation, the wavelength of the emitted light is dependent on its temperature. Hotter objects emit more light in the blue and ultraviolet part of the spectrum, while cooler objects emit more in the red and infrared. At 2740 K, R Doradus radiates most of its light in the infrared spectrum, with only a modest amount spilling into the visible red. This deep red glow is the signature of a star nearing the end of its life cycle. In the grand stellar narrative, a star like R Doradus began as a main sequence star, much like our Sun, burning hydrogen into helium in its core. For billions of years, it sustained a delicate balance between gravitational collapse and nuclear pressure. But like all things in the universe, the supply of hydrogen was not infinite. Eventually, the core ran low, and with that depletion came a cascade of changes. The core began to contract under gravity, heating up and igniting a new phase of nuclear fusion in the surrounding shells of material. Meanwhile, the outer layers began to swell and cool, leading to the transformation into a red giant. The red color, then, is the physical manifestation of these cosmic changes. It's the chromatic echo of hydrogen exhaustion and helium fusion, the visual signpost of a star that's bloated with age. R Doradus is no longer the efficient, stable engine it once was. It's now a swollen envelope of gas and plasma, tenuously held together, expanding and cooling as it slowly drifts toward its final fate. But there's more embedded in that hue than just temperature. The red glow of R Doradus is also influenced by the composition of its atmosphere and the presence of molecules and dust in the region surrounding the star. These molecules absorb and re-emit radiation at particular wavelengths, further emphasizing the star's red and infrared character. Molecules like titanium oxide, water vapor, and carbon monoxide, which can't survive in hotter stars, can form in the relatively cool upper atmosphere of R Doradus. These molecules absorb visible light in particular bands, enhancing the red tones and deepening the visual character of the star. And the red color isn't static, it's dynamic, just like the star itself. R Doradus is a semi-regular variable star, meaning its brightness fluctuates over time. These pulsations are not just in brightness, but in temperature and radius as well. As the star expands, its surface cools slightly and becomes redder. As it contracts, the surface heats slightly and becomes somewhat less red. The rhythm of these changes, on a scale of several hundred days, adds a pulsating quality to the red light, like a slowly beating cosmic heart. In many ways, the color of R Doradus mirrors its identity as a dying star. It's no longer burning bright and blue like the young, massive stars in Orion's belt. It no longer shines with the yellow-white stability of middle-aged stars like our Sun. Instead, its red glow is soft, ancient, and melancholic. It's the color of a star that has lived a long life and is now casting its outer layers into the void, enriching the cosmos with the materials that may someday coalesce into planets, moons, and perhaps life. In the broader context of astronomy, red giants like R Doradus are part of an important evolutionary bridge. They serve as the transitional phase between the calm stability of main sequence stars and the final white dwarf remnants that come later. The red color marks this bridge, this moment when the star is no longer young but not yet gone. It's the chromatic middle passage of stellar life. What makes R Doradus even more intriguing is how its red hue shifts dramatically when viewed in different parts of the electromagnetic spectrum. To the human eye, under optimal viewing conditions, it might appear as a dim orange or red point. But to an infrared telescope, the star is astonishingly bright, a fiery beacon. In infrared images, the color takes on a different role. It becomes a measure of heat energy invisible to our eyes but very real in the physical universe. This underlines the fact that our perception of color, based on visible wavelengths, only tells a small part of the story. The true color of R Doradus in a physical sense is dominated by the infrared, heat energy pouring off its massive, bloated surface. The redness of R Doradus is not just aesthetic, it's deeply symbolic. It represents entropy, decay, and change. But in that change lies creation. The material being shed from its outer layers will mix into the interstellar medium, providing the carbon, oxygen, nitrogen, and silicon that will form the next generation of stars and planets. So even in its red decline, R Doradus is not ending, it's transforming, evolving, contributing. There's something almost poetic in that, a giant, dying star glowing softly in crimson, whispering its legacy into the darkness. Not all deaths are violent. Some are slow, dignified, and red. Though R Doradus might slip by unnoticed to the naked eye, just a faint ember in the sea of stars, it becomes something entirely different when we shift our gaze into the infrared. There, hidden beyond human sight, it transforms into a titan of radiance. Despite its dimness in visible light, R Doradus is one of the brightest celestial objects in the entire sky when viewed in the infrared spectrum. It's not merely brighter than average, it is ranked among the top few brightest stars in Earth's infrared sky, sometimes second only to Betelgeuse. To understand why, we need to consider how stars emit light. Most people are familiar with the concept that stars like our Sun emit most of their energy in visible wavelengths. But cooler stars, like red giants, radiate differently. Due to its relatively low surface temperature, R Doradus emits the majority of its energy as long-wavelength infrared radiation. These infrared rays are invisible to our eyes, but they carry immense amounts of energy and information. They are the glowing warmth of the star's bloated atmosphere, stretching across vast distances of space. This dominance in the infrared is what makes R Doradus such a valuable target for observatories like the Spitzer Space Telescope or the Atacama Large Millimeter/Submillimeter Array, ALMA. These telescopes are specially designed to detect and analyze light that our eyes, and even traditional optical telescopes, cannot see. In their eyes, R Doradus isn't faint at all. It blazes with intensity, standing out sharply against the cold backdrop of space. Why is it so bright in the infrared? The answer lies in both the temperature and sheer size of the star. While it's cool relative to stars like the Sun or blue giants, the surface area of R Doradus is absolutely colossal. It has over 120,000 times the surface area of the Sun. That enormous skin radiates energy, and though each square meter of its surface emits less energy than the Sun's, the total output adds up to a brilliant infrared glow. Furthermore, R Doradus's extended atmosphere and surrounding dust shell act like a secondary emitter. Dust particles surrounding the star absorb some of the outgoing light and re-radiate it as thermal infrared energy. This process, known as thermal re-radiation, boosts the overall infrared brightness of the star. In essence, R Doradus doesn't just glow with its own light, it creates a kind of infrared halo, expanding its footprint far beyond the photosphere. This brightness in the infrared makes it an incredibly useful calibration point for astronomers. In fact, R Doradus is often used as a standard candle or reference object in infrared astronomy. Because it's so nearby, well-studied, and consistent in its behavior, at least compared to more chaotic variables, it serves as a kind of infrared lighthouse for telescopes scanning the skies. Scientists can compare distant or fainter stars to R Doradus to determine properties like luminosity, distance, and dust content. Its prominence in the infrared also opens a window into parts of the cosmos that are otherwise hidden. Infrared light is particularly good at penetrating interstellar dust, which blocks visible light. In regions of the galaxy where thick clouds of dust obscure optical observations, infrared bright stars like R Doradus shine through, acting as beacons that reveal the structure of our galaxy and the nature of star-forming regions. There's also a practical and historical reason R Doradus became such a standout in infrared astronomy. It was an early subject in many of the first infrared sky surveys. During the 1980s and 1990s, with the launch of infrared observatories like the Infrared Astronomical Satellite, IRAS, and later Spitzer, R Doradus consistently appeared as one of the brightest infrared sources in the southern sky. This prominence wasn't just statistical, it made the star an early benchmark in understanding cool star atmospheres, mass loss processes, and circumstellar dust chemistry. It's easy to overlook the significance of being bright in infrared, especially since most people never directly see infrared light. But for astronomers, this kind of brightness is gold. It means more data, clearer images, and the ability to study subtle features like molecular bands, stellar wind velocities, and even the shapes of the outer atmosphere. R Doradus has also helped refine our models of stellar opacity and radiative transfer, the physics of how light moves through the atmospheres of stars. Because the infrared light from R Doradus passes through cool gases and molecular layers, it carries the imprints of everything it touches. Astronomers can decode these imprints to learn about temperature gradients, dust composition, gas dynamics, and even the presence of exotic molecules that can't survive in hotter environments. This hidden brilliance challenges the way we think about stars. It's a reminder that the human eye, marvelous as it is limited. What we perceive as dim and forgettable might, in another wavelength, be among the most luminous entities in our sky. It humbles us, reminding us that the universe is vast not just in space, but in spectrum. What R Doradus lacks in visible spectacle, it more than makes up for in infrared majesty. It also gives rise to a deeper philosophical reflection. How many other such giants blaze unseen, their stories unspoken because we're looking with the wrong eyes? How many mysteries are locked in the wavelengths we don't instinctively perceive? R Doradus teaches us not just about dying stars, but about the importance of perspective. To truly understand the universe, we must look beyond the narrow sliver of light our biology allows and embrace the full range of the cosmos. So while you may not notice R Doradus on your next stargazing night, rest assured, out there in the southern sky, one of the brightest infrared beacons of the heavens is pouring light across the void, unseen but never insignificant. Despite its immense size, powerful infrared brightness, and proximity to Earth, R Doradus remains a ghost in the public consciousness, almost entirely unknown outside of astronomical circles. It hasn't earned the mythological allure of Orion's Betelgeuse or the mainstream recognition of Polaris, the North Star. For many, even passionate stargazers, R Doradus simply doesn't exist in their mental map of the sky. So how can a star so large and nearby be so obscure? The reasons for this mystery are rooted in two main factors: its position in the southern sky and its low brightness in the visible spectrum. Together, these make R Doradus one of the most scientifically significant yet publicly invisible stars in the galaxy. First, let's consider geography. R Doradus lies in the constellation Dorado, which is only visible from the southern hemisphere and very low in the horizon from extreme southern parts of the northern hemisphere. If you live north of the equator, anywhere in Europe, North America, or most of Asia, this star never even rises above your local horizon. It remains permanently hidden by the curvature of Earth, like a secret whispered only to the southern half of humanity. This simple fact has massive implications for awareness. Astronomy, historically, has long been biased toward the northern hemisphere. The most ancient observatories, early star maps, and classical constellations all developed from civilizations north of the equator. The myths, all centered on northern skies, became the foundation of popular astronomy, a legacy that persists in how we name stars and recognize constellations. Dorado, by contrast, is a relative newcomer, introduced in the late 16th century by Dutch navigators exploring the southern seas. So for centuries, R Doradus simply wasn't visible to the majority of the world's astronomers, or anyone else for that matter. Only with the expansion of astronomical infrastructure into the southern hemisphere, in places like Chile, South Africa, and Australia, has this hidden giant begun to receive the attention it deserves. The second reason for its obscurity is even more frustrating: its low visible brightness. R Doradus typically hovers around a magnitude of 5.0 to 6.6, fluctuating due to its semi-regular pulsations. While this range technically puts it on the edge of naked eye visibility under pristine dark skies, it's usually drowned out by urban light pollution, moonlight, and atmospheric interference. In cities or suburbs, even well-prepared observers would struggle to pick it out without optical assistance. To the casual eye, R Doradus simply disappears. There's also a deceptive quality to how stars are perceived. People often equate importance with brightness. The stars that dominate public imagination, Sirius, Vega, Rigel, are bright in the visible spectrum, standing out like diamonds on a black canvas. They are photogenic and dramatic, easily visible with no equipment, and often central to familiar constellations. R Doradus, in contrast, doesn't participate in any major star pattern or align with popular celestial landmarks. It's isolated, both geographically and visually. Another subtle factor is the nature of human perception itself. The human eye is less sensitive to red light, especially under low-light conditions. Known as the Purkinje effect, this phenomenon causes the eye to become more sensitive to blue and green light in dim environments, while red objects seem to fade. As a red giant, R Doradus suffers from this quirk of biology. It simply appears dimmer than it is because our eyes are not optimized to detect its color. Moreover, because R Doradus emits most of its radiation in the infrared, it does not project the visual dominance it deserves. Even a smaller star with a higher surface temperature might outshine it in the optical band, fooling observers into thinking it's more significant. This mismatch between true luminosity and apparent brightness is another way R Doradus hides in plain sight. Then there's the fact that R Doradus doesn't behave in a way that demands attention. It's not part of a brilliant binary system like Sirius. It's not a dramatic variable like Mira, whose changes in brightness are so extreme they're easily noticeable even without instruments. Nor is it a supernova candidate like Betelgeuse, which caused global excitement when it dimmed significantly in 2019. R Doradus is relatively calm, semi-regular, and stable in comparison. Its subtle pulsations and modest variability make it a topic of deep scientific interest, but not the kind of star that makes headlines. Finally, it's worth acknowledging the role of popular media and education. The stars that become household names often do so through exposure, books, films, educational programs, and cultural narratives. Betelgeuse appears in science fiction. Polaris is taught in schools. R Doradus, though immensely significant to astrophysicists, simply hasn't received the cultural spotlight. Without stories, or visual spectacle, it's been passed over in favor of flashier stars with easier names and more dramatic behaviors. But what makes R Doradus's anonymity so fascinating is how it contrasts with its actual physical importance. In the realm of stellar evolution, infrared astronomy, mass loss studies, and late-stage stellar dynamics, it is a key player. It serves as a living laboratory for everything we want to know about the future of our sun and the mechanics of dying stars. It's a workhorse for testing theories of convective dynamics, dust formation, and stellar winds. And it's one of the few stars where we can resolve surface details directly using interferometric imaging, a scientific treasure trove hidden behind a veil of dim red light. So R Doradus is a paradox, too big to ignore yet too dim to notice. Too close to be unknown, yet too southern to be seen. Its story is not one of dramatic explosions or dazzling brightness. It is the story of a quiet colossus, glowing gently in obscurity, waiting for those who know where and how to look. In the grand architecture of our Milky Way galaxy, spanning over 100,000 light-years across, with hundreds of billions of stars swirling in a majestic spiral, distances can be deceptive. When we say R Doradus is about 200 light-years away, that might sound remote to the uninitiated. After all, light traveling at nearly 300,000 kilometers per second still takes 2 centuries to reach us from this red giant. But in astronomical terms, R Doradus is practically next door. It resides firmly within our local stellar neighborhood, part of a small, cozy bubble in the galactic disk known as the local bubble, which houses our sun and many of the stars we are most familiar with. To place this in context, our Milky Way contains a vast range of star types spread across different regions, dense star-forming regions like the Orion Arm, crowded globular clusters in the galactic halo, and remote stars in the outer rim. Against this backdrop, 200 light-years is exceptionally close. Many of the stars that we see in the night sky are hundreds, or even thousands of light-years away. Deneb in the constellation Cygnus is over 2,600 light-years away. Antares, another famous red giant, is around 550 light-years distant. In contrast, R Doradus is so close that light we receive from it today began its journey in the early 19th century, a time when steam engines were just beginning to revolutionize human civilization. This proximity is not just a trivial statistic, it carries profound observational advantages. At this distance, astronomers can resolve features on and around the star that would be impossible to detect in more distant giants. It's one of the few red giants where techniques like optical interferometry can be used to literally see the surface, not as a point of light, but as a disk with texture, granulation, and asymmetry. It also means that the movement of the star through space, its velocity relative to our solar system, and its changes in brightness and shape can all be monitored with fine precision. R Doradus shares this cosmic region with other notable nearby stars, forming part of what astronomers call the solar neighborhood, a region roughly 1,000 light-years in diameter that contains our Sun and several thousand other stars. Among these are stars like Alpha Centauri, our closest stellar neighbor at just 4.37 light-years away, Tau Ceti at 12 light-years, and Epsilon Eridani at around 10.5 light-years. These are all Sun-like stars, relatively small, stable, and visually bright. But in this mix of ordinary main-sequence stars, R Doradus stands out dramatically due to its enormous physical size and unique stage of evolution. Most of the stars within 200 light-years are main-sequence stars, those still burning hydrogen steadily in their cores. Very few red giants reside this close to Earth, and even fewer are as massive, extended, or bright in the infrared as R Doradus. In fact, among red giants within this range, it is one of the largest and most luminous in the sky. Its presence so near to us makes it a natural laboratory for studying late-stage stellar evolution. Astronomers can use it to calibrate their models of how stars evolve, how they lose mass, and how their internal structures shift as they age. And because it's relatively close, data from R Doradus is cleaner and more detailed than what we can gather from more distant giants whose light has been scattered and reddened by the interstellar medium. Its motion through space also tells us about the kinematics of stars in the local Milky Way. R Doradus is drifting through the galaxy with its own proper motion, a slow arc across the sky that becomes apparent only after decades of observations. This motion can be tracked precisely using astrometry, revealing not just its trajectory but also how it interacts gravitationally with surrounding stars and gas. It's a puzzle piece in our effort to understand the dynamics of stellar populations near the Sun. It also serves as a contrast point. By studying R Doradus and comparing it with other nearby stars, particularly smaller red dwarfs or midlife Sun-like stars, astronomers can piece together the timeline of stellar life. R Doradus shows us what happens near the end of a star's lifespan, while stars like Alpha Centauri or Procyon illustrate earlier phases. Together, these neighbors offer a 360-degree view of stellar evolution, made possible only because of their relative closeness. This closeness also has an emotional impact. When we talk about distant galaxies, black holes, or quasars, they often feel abstract, cosmic curiosities far removed from everyday reality. But a star like R Doradus? It's near enough to feel real, tangible. We know that if our eyes could see an infrared, we'd see it as one of the dominant beacons in the southern night. And if we could travel at the speed of light, it would take only 2 centuries to visit. That's close enough that our descendants could send probes or signals and receive data back within a few generations. There's a quiet intimacy in knowing that such a massive, dying star exists within such a short reach of our solar system. It's like living down the street from a volcano, not one that threatens, but one that fascinates. A gentle giant aging gracefully in the cosmic twilight, close enough to watch, learn from, and contemplate. In short, R Doradus is not just part of the cosmic canvas, it's one of its most compelling brushstrokes, painted right within arm's reach of our tiny pale blue dot. One of the most captivating aspects of R Doradus, beyond its size, proximity, and infrared brilliance, is that it's not a steady beacon. Instead, it pulses, breathes, and subtly flickers in brightness over time. It's what astronomers classify as a semi-regular variable star, and that variability adds another layer of complexity to its already fascinating character. Semi-regular variable stars are stars whose brightness fluctuates in a relatively predictable, though not entirely consistent, pattern. R Doradus falls into this category, meaning that its light output increases and decreases over periods of weeks to months, not chaotically, but with discernible rhythms. These stars are different from strictly periodic variables like Cepheids or RR Lyrae stars, whose changes in brightness are remarkably consistent. Instead, semi-regulars like R Doradus exhibit quasi-regular patterns. Sometimes the brightness changes follow a dominant cycle, other times, secondary or overlapping cycles muddy the waters, creating a light curve that feels almost like a heartbeat skipping a beat now and then. For R Doradus, the primary period of variability is roughly 332 days, a cycle just shy of one Earth year. During this time, its brightness waxes and wanes in a slow, languid rhythm. This change is visible in the star's apparent magnitude, which can vary from about 5.0 down to 6.6. Under perfect dark skies, the brighter phase can be seen with the naked eye, while during dimmer periods, a telescope or binoculars might be needed to spot it. These changes are subtle compared to the dramatic dimming of stars like Mira, which can vanish from naked eye view entirely, but they are consistent enough to track, making R Doradus a favorite among amateur and professional astronomers who monitor variable stars. So what causes this stellar flickering? The changes in brightness are not due to eclipses by a companion star, like in an eclipsing binary system, nor are they the result of sunspots or magnetic storms like we see on our own Sunday. Instead, they arise from pulsations in the star's outer layers. R Doradus, being a red giant, has an extended and loosely bound outer envelope. As nuclear processes shift within its interior, pressure waves travel outward, causing the star to expand and contract in a slow, majestic rhythm. During expansion phases, the star's surface area increases, but its temperature drops slightly, changing its luminosity and the spectrum of light it emits. In contraction phases, the surface tightens, heats slightly, and becomes marginally more luminous in visible wavelengths. These changes, occurring over months, are enough to alter the amount of light we receive from Earth. Interestingly, this variability is not only a function of pulsation. Convection, the churning, boiling movement of plasma near the surface, plays a significant role too. Giant convective cells, far larger than anything seen on the Sun, can emerge, move, and dissipate over time, subtly altering the star's appearance and brightness. These convective processes don't follow perfect schedules, adding a chaotic edge to the otherwise rhythmic pulsations. Sometimes, this interaction leads to shifts in the timing or amplitude of brightness variations, causing the star to behave unpredictably from one cycle to the next. What's even more fascinating is that this variability occurs alongside other subtle phenomena. Some astronomers have reported multiple overlapping periods in R Doradus's light curve, suggesting that the star doesn't just pulse in a single mode. It may vibrate simultaneously in fundamental and overtone modes, much like a bell ringing at more than one frequency. These multiple pulsation modes create beat patterns, where the light seems to rise and fall in complex sequences over several years, adding even more richness to its behavior. For observers, tracking this variability is more than a curiosity. It's a window into the star's internal structure and dynamics. By studying the timing, shape, and intensity of the pulsation cycles, scientists can model the star's density, composition, and evolutionary status. These light variations serve as a kind of non-invasive stellar echocardiogram, giving us insight into a body we can't directly touch. Furthermore, variability has another consequence. It affects the star's mass loss processes. During the expansion phases, the star's outer layers become even more tenuously held, allowing stellar winds to blow off more easily. These pulsations essentially act as a kind of stellar bellows, rhythmically pumping material into the surrounding space. That material, full of dust and molecules, contributes to the glowing shell around the star and enriches the interstellar medium. Because R Doradus is relatively close, we can observe these pulsations with extraordinary detail. Instruments have captured the slight changes in radius and brightness over time, and radio and infrared telescopes can detect the shifts in molecular absorption lines caused by moving layers of gas. Some observations have even captured subtle asymmetries, regions where the star is brighter or darker, suggesting giant convective cells or localized bright spots. Amateur astronomers also participate in tracking its variability. Organizations like the American Association of Variable Star Observers, AVSO, collect data from thousands of skywatchers worldwide who log brightness estimates night after night. Over years and decades, these logs form rich time series datasets that allow scientists to detect long-term trends and changes in behavior. R Doradus, being both variable and relatively easy to find from southern latitudes, is an ideal candidate for this kind of monitoring. Even though it doesn't flicker dramatically from night to night, its subtle rhythm becomes apparent over months. Observers often describe it as watching a giant organism breathe slowly, expanding and contracting, glowing and fading, as if alive. It is not the frenetic pulse of a young star or the violent heartbeat of a dying supernova, but the measured, ancient breath of a star in its twilight years. This variability is not just a scientific feature, it is a poetic one. R Doradus is not a static entity frozen in space, but a dynamic, changing being. Its light tells a story not of permanence, but of ebb and flow, of rise and fall, of life and motion even as it nears its end. And through this rhythm, we are reminded that the cosmos itself is never still. It pulses with time, with life, and with change, on scales far beyond human perception, yet no less real. While R Doradus belongs to the family of pulsating red giants, it sits in a more nuanced class when compared to its more dramatic cousins, specifically, the Mira variables. Named after the star Mira, Omicron Ceti, these celestial giants represent a particularly extreme subset of long-period variable stars, exhibiting massive fluctuations in brightness over regular intervals. Mira itself, for instance, can brighten by a factor of 1,500 during its cycle, transitioning from total invisibility to naked eye prominence every 332 days or so. But R Doradus, though rhythmically pulsing in its own right, doesn't go to such extremes, making it a softer, subtler variation on a similar theme. Both R Doradus and Mira stars are aged red giants, specifically asymptotic giant branch, AGB stars, nearing the final stages of stellar evolution. They are stars that have exhausted the hydrogen in their cores and are now burning helium and other heavier elements in shells around a core composed of carbon and oxygen. These stars are bloated, cool, and highly luminous, with huge, distended outer envelopes barely held together by gravity. But despite these commonalities, Mira variables exhibit greater regularity and amplitude in their light curves. R Doradus is classified as a semi-regular variable, SRB type, while Mira is a classic Mira-type, M-type, variable. The distinction is important. Mira-type variables have highly periodic, predictable brightness changes with amplitudes that exceed 2.5 magnitudes in visible light. They brighten and fade with such consistency that they served as some of the first standard candles in the history of astronomy, helping astronomers estimate distances to other galaxies before Cepheids took center stage. In contrast, R Doradus pulses on a similar timescale, about 332 days, but its amplitude of variability is much lower, typically less than 1.5 magnitudes. This means that while Mira can almost vanish from the night sky and then return as a brilliant point of light, R Doradus merely shifts from faint to fainter. Its variability is discernible with instrumentation or long-term observation, but it doesn't create the same visual drama. This gentler behavior offers a rich observational opportunity. Unlike Mira variables, which can be difficult to observe during their dimmest phases, R Doradus remains accessible for most of its pulsation cycle, especially to infrared and radio telescopes. Its variability is semi-regular, meaning there is a dominant period, around 332 days, but also secondary fluctuations layered on top. This makes R Doradus an excellent example of multiperiodic pulsation, where a star doesn't vibrate in a single simple mode, but oscillates in complex patterns, much like a drumhead struck in several places at once. The comparison between R Doradus and Mira also provides insight into the diversity of stellar behavior on the AGB. While all these stars are undergoing dramatic internal changes and losing mass into space, the manifestations of those changes differ based on mass, chemical composition, and evolutionary timing. Mirror-type stars are typically further along in their evolution or perhaps slightly more massive, having reached a state where their internal instabilities produce higher amplitude pulsations. R Doradus may represent an earlier or less intense stage of this evolutionary journey, making it an invaluable case study for understanding how red giants gradually become mirror-type stars, or why some never do. Another key point of comparison lies in their mass loss mechanisms. Mirror variables often have dense, dusty circumstellar shells, created by powerful pulsations that lift material away from the stellar surface. These shells often obscure visible light entirely, making the stars almost invisible in optical wavelengths at their dimmest. R Doradus, by contrast, while still losing mass and generating dust, does so at a more moderate rate, producing a thinner shell that allows much of its radiation, especially infrared, to escape with less attenuation. This makes it less obscured, more stable, and easier to study in multiple wavelengths across the electromagnetic spectrum. Chemically, both Mira and R Doradus stars are oxygen-rich, meaning their atmospheres have more oxygen atoms than carbon. This chemical signature affects the kinds of molecules that form in their atmospheres, favoring silicates, water vapor, and metal oxides, and contributes to the formation of oxygen-bearing dust grains. However, the less intense pulsation of R Doradus results in a more stable atmosphere where rare molecules like TiO, titanium oxide, H2O, and CO can persist and be observed without being immediately driven off or masked by chaotic dust production. And then there's the matter of observability. Mirror-type stars often become enveloped in thick shells of ejected gas and dust, rendering them invisible in the optical band and limiting study to infrared or radio wavelengths. R Doradus, with its comparatively clear outer shell, allows for high-resolution imaging of its surface features, pulsations, and circumstellar environment. It's been observed using interferometry, where multiple telescopes work in tandem to resolve surface structure, and with ALMA, to trace the movement and composition of the material it sheds. These observations help us understand how mass loss begins, before it ramps up into the dramatic outflows seen in true mirror-type stars. So in essence, R Doradus may not be as flashy as Mira, but it offers a more approachable and instructive window into the processes that dominate the lives of dying stars. It's the more measured cousin, not caught in the violent throes of its final convulsions, but still pulsing, still shedding, still telling the story of stellar aging in a quieter voice. Its very moderation makes it a bridge between regular red giants and the wild, turbulent mirrors, an intermediate phase in a sequence that ends in planetary nebulae and white dwarfs. R Doradus teaches us that not all dying stars go out in a blaze. Some fade, fluctuate, and surrender slowly, giving us time to observe and learn before the final light slips away. It is, in many ways, a mirror that hasn't yet screamed, a cousin with a softer tone, but no less fascinating for it. Imagine a heart the size of a star, one that beats not in seconds, but in a slow, almost meditative rhythm that takes nearly a full Earth year to complete. That's the essence of R Doradus. With a pulsation period of approximately 332 days, this giant red star breathes in and out across time, expanding and contracting in a cycle so vast that it defies our everyday sense of motion. It is not a flicker. It is a cosmic inhale and exhale, the kind of rhythm one might attribute to a living, sentient being rather than a nuclear furnace drifting through space. This slow, stately pulsation is not a superficial shimmer or a fluctuation on the surface. It's a deep-seated, structural transformation. Over those 332 days, R Doradus undergoes subtle but real changes in size, temperature, and brightness. At the peak of its cycle, the star swells to its largest size, its surface cooling slightly due to expansion. This is when it is most extended, its photosphere, or surface, pushing outward into space. And then the reverse begins. The outer layers contract, drawn inward by gravity as internal pressures drop. This contraction slightly increases the temperature of the outer shell, leading to an uptick in brightness before the process begins again. The pulsation cycle is not perfectly symmetrical, and this asymmetry is crucial. Like a balloon that inflates and deflates unevenly, R Doradus's light curve doesn't form a perfect sine wave. There are steeper rises, gentle declines, plateaus, and troughs, all of which encode details about the star's internal mechanics. It's as if the star is not simply beating, but sighing, hesitating slightly between each breath, giving us time to observe the nuances of its respiration. What drives this cycle is not just surface motion. The pulsations are triggered by thermal instabilities deep within the star, caused by the energy transport processes in its layered, shell-burning interior. Unlike main-sequence stars that burn hydrogen in a stable core, red giants like R Doradus rely on shells of hydrogen and helium fusing in layers around a degenerate carbon-oxygen core. These shells are unstable. When enough pressure builds up in a shell, it can ignite in a thermal pulse, sending pressure waves outward that ripple through the vast convective envelope, driving expansion. Once the pressure dissipates, gravity draws the outer layers back in. This entire dance results in the star breathing, slowly, steadily, and for thousands or even millions of years. The 332-day pulsation period of R Doradus places it right at the edge of the Mira class of variables, whose pulsation periods typically exceed 100 days and whose brightness changes can be extremely dramatic. While R Doradus doesn't reach the visual extremes of Mira, its pulsation is robust enough to be felt and tracked, and it shares many of the internal mechanisms that power these long-period pulsators. During each pulsation, the radius of the star can vary noticeably, by a factor of up to 10 to 20% or more. For a star already over 350 times the diameter of the Sun, this kind of rhythmic swelling and shrinking is astonishing. Imagine the orbit of Mars being traced in and out over the course of a year, not by a planet, but by the outer shell of a breathing, massive star. This breathing also stirs up the star's outer layers, affecting the chemistry and dynamics of its atmosphere. As the star expands and cools, molecules such as H2O, CO, and CO form in the cooler layers, while contraction can destroy or redistribute these compounds. The pulsation acts like a cosmic stirrer, constantly mixing the gases and molecules in its envelope, allowing astronomers to detect varying molecular signatures at different phases of its cycle. Even the winds from R Doradus, its slow, steady loss of mass into space, are influenced by this breathing rhythm. As the outer atmosphere swells, stellar winds intensify, driving dust and gas away from the star. These winds are not uniform, but modulated by the pulsation cycle, creating rippling outflows that shape the star's eventual planetary nebula. Each breath is like a subtle exhalation, a whisper of future dust clouds that will someday drift across the galaxy. From Earth, this pulsation is seen as a gradual dimming and brightening in the visual and infrared wavelengths. The star's brightness doesn't change randomly. It changes in sync with its internal pressure waves, creating a pattern that can be plotted, predicted, and studied. Astronomers monitor R Doradus with light curves, precise plots of brightness over time, which reveal the cyclical nature of its activity. And yet, like the breathing of a person with a unique rhythm, no two cycles are exactly alike. Variations occur. Some pulses are more intense. Some intervals are longer. These inconsistencies may stem from convection cells, shock waves, or even magnetic field interactions within the stellar atmosphere. Interestingly, this rhythmic behavior is not forever. R Doradus is in a transitional phase of its life. As it ages and continues to shed its mass, its internal structure will change, potentially altering its pulsation period. It might become more like a Mira variable, increasing its pulsation amplitude and becoming less stable. Or it might collapse into a more irregular state before shedding its outer layers entirely, and transforming into a white dwarf. In that sense, its current 332-day cycle is a snapshot in time, a temporary rhythm that will eventually shift as the star's internal dynamics evolve. And yet, while it breathes, R Doradus offers something profound. It transforms the abstract notion of stellar evolution into something tactile, alive, and temporal. Stars are not just distant spheres of plasma. They are entities with motion, with cycles, with lives that can be mapped in time. R Doradus beats with a rhythm that our instruments can trace, a heartbeat we can watch unfold year after year. This sense of life, of motion, of breath, these are the qualities that make R Doradus feel less like an object and more like a being. A giant, ancient creature suspended in the void, pulsing gently, as if asleep. Watching R Doradus is like watching a slow tide, a celestial tide with a pulse that resonates across centuries. It reminds us that even the largest things in the universe move with grace, with tempo, and with the kind of silent power that only the stars possess. To truly grasp the wonder of R Doradus's pulsing nature, we must go beneath its fiery outer shell. When we say that a star like R Doradus pulses, it's tempting to imagine something happening solely on its surface, like ripples on a pond or solar flares lashing out into space. But in truth, this pulsation runs far deeper. It is not a superficial event. It is a profound, internal phenomenon driven by the star's own structure and the subtle balance between pressure and gravity, a rhythm born from the star's core, traveling through its vast and loosely held envelope, affecting every layer from inside out. R Doradus, like other red giants, is no longer in the calm, stable state it once occupied during its main sequence life. Back then, it fused hydrogen into helium in its core, producing a steady outward pressure that balanced gravity's inward pull. But that equilibrium ended long ago. Now, having exhausted hydrogen at its core, the star burns helium in a shell around a degenerate core of carbon and oxygen, with additional shells of hydrogen burning further out. This layered fusion, with each shell operating under different conditions, sets the stage for pulsations. These pulsations are not mere temperature shifts or surface flickers. They are waves of pressure, global oscillations that travel through the entire star. Astronomers call this process radial pulsation, meaning the star expands and contracts symmetrically in all directions, like a balloon that grows and shrinks repeatedly without distorting its shape. During expansion, pressure builds from within, perhaps due to the temporary ignition of helium or a sudden change in opacity within the star's layers, causing the star's outer regions to push outward. This expansion cools the surface, dims visible light, and increases infrared output. Then, as the internal pressure subsides and gravity takes over again, the star contracts, heating slightly and brightening in the visible range once more. It's a grand breathing cycle, but what makes it most astonishing is that this entire stellar body, this object hundreds of times the diameter of the Sun, participates in the movement. The outer atmosphere doesn't just flutter, it rises and falls by millions of kilometers. In terms of physical scale, this would be like Earth's atmosphere not only expanding upward but doing so until it brushed the Moon, then collapsing back toward the planet in an invisible, graceful dance. But for R Doradus, such expansion and contraction are normal. These changes happen over the course of hundreds of days, but they involve motion on a scale beyond comprehension, entire shells of stellar material lifting and falling, pushed by waves that originated deep within the fusion furnaces at its core. At the heart of this phenomenon is a process known as the kappa mechanism, which is believed to drive many pulsating stars. The kappa mechanism hinges on how opacity, or the ability of a star's material to trap light, changes with temperature and pressure. In certain layers of the star, particularly in ionized zones, an increase in compression leads to higher temperatures and greater opacity. This traps radiation, builds up internal pressure, and causes that layer to expand. As it expands, it cools, its opacity decreases, radiation escapes, and gravity reasserts itself, pulling the layer back in. This cycle of light trapping and releasing acts like a spring being compressed and released, driving rhythmic pulsation throughout the star. For R Doradus, these pulsations also involve convection and molecular chemistry. Unlike smaller stars, red giants have massive convective envelopes where huge plumes of hot plasma rise and fall, transporting energy outward like slow-moving geysers. These convective motions, combined with the pulsation waves, produce complex interactions. The upper atmosphere becomes a turbulent zone of shock waves, rising gas, and falling material. Molecules like water vapor and carbon monoxide can only exist in certain temperature ranges, and the pulsations create temperature shifts that allow these rare molecular layers to form and reform cyclically. And these internal waves are not silent. As they travel, they leave behind traces in light, velocity, and spectra. Telescopes using Doppler shift measurements can detect the oscillating velocities of the star's surface, revealing how layers are moving toward or away from Earth. In some phases, the surface can move outward at several kilometers per second, In others, it collapses inward with similar speed. These are not sound waves in the traditional sense, but they resemble acoustic waves, standing pressure waves that set the whole star ringing like a bell, albeit one with notes measured in months rather than seconds. Thanks to instruments like interferometers and high-resolution spectrometers, scientists have been able to peer into these pulsations in great detail. The Atacama Large Millimeter/Submillimeter Array, ALMA, for example, has mapped the distribution of molecules in R Doradus's extended atmosphere, revealing the layered shells that pulse outward in step with the star's cycle. Each expanding wave carries material with it, pushing molecules and dust further into space. These waves are not abrupt like explosions, but slow surges, like the rolling of tides or the stretching of a living organism as it exhales. Pulsation is not a sign of instability in the catastrophic sense. Rather, it's a sign of maturity, of a star adjusting to the physics of aging. Just as a beating heart reflects the vitality of a body, R Doradus's rhythmic changes reflect the ongoing tension between gravity and pressure, fusion and collapse, radiation and opacity. The whole star is engaged in this cyclical motion, not just the surface, not just the visible edge, but from deep inside out to its dusty, translucent envelope. It's also essential to understand that this internal motion will one day come to an end. As R Doradus continues to lose mass and burn through its remaining fuel, the internal pressures that drive these pulsations will diminish. The fusion shells will flicker and extinguish. The gravity-bound core will stabilize as a white dwarf, and the surrounding material, pushed outward over millennia by countless pulsation cycles, will drift away as a planetary nebula. The pulsing will stop. The breath will cease. What remains will be a dense ember, no longer expanding or contracting, but forever holding the memory of a star that once moved like a living, breathing thing. So when we speak of R Doradus's pulsations, we are not merely describing fluctuations in brightness. We are observing the last breaths of a stellar giant, powered by forces deep within, echoing outward across space. Each pulsation is a message sent into the cosmos, a signal that the star is alive, aware in its own nuclear way, reshaping itself as it approaches its twilight. Despite its immense size and brightness in the infrared, R Doradus is surprisingly cool. In fact, its surface temperature is one of its most defining characteristics, a trait that helps classify it as a red giant and explains its deep, ruddy glow. The surface, or photosphere, of R Doradus hovers at approximately 2,740 Kelvin, which is drastically cooler than the Sun's surface temperature of about 5,778 Kelvin. That difference, over 3,000 degrees, makes R Doradus appear as an ember rather than a blaze when viewed in the visible spectrum. Yet despite its comparative coolness, its sheer surface area allows it to radiate an astonishing amount of energy. This low temperature is what gives R Doradus its rich red-orange hue, the signature coloration of aging, expanded stars nearing the ends of their lives. As stars cool, the peak of their light emission shifts toward the red and infrared parts of the spectrum. That's why, though R Doradus doesn't shine impressively to the naked eye, it becomes a brilliant object in the infrared. Its temperature sits right at the threshold where visible red and infrared overlap. This means we don't see the full glory of its luminosity unless we look through specialized detectors that can sense longer wavelengths of light. But the temperature figure, 2,740 K, only tells part of the story. While it offers an average for the photosphere, the outer layers of R Doradus are not uniform. Stars like this are not smooth, symmetrical spheres. Their vast atmospheres are often lumpy, turbulent, and unstable, with localized regions of different temperatures. Some patches may be cooler by hundreds of degrees, while others might be hotter, possibly due to giant convection cells, massive, slow-moving bubbles of hot gas rising and falling like the surface of a boiling liquid. The lower temperature also means that many complex molecules can form and survive in the outer atmosphere of R Doradus. On the Sun, with its intense heat, molecules are torn apart almost instantly. But in the cooler atmosphere of a star like R Doradus, you can find molecular bands of water vapor, H2O, carbon monoxide, CO, silicon monoxide, CO, titanium oxide, TO, and even metal hydrides. These molecules absorb and emit light in specific infrared bands, making R Doradus a treasure trove for infrared spectroscopy. When astronomers peer into its light through instruments like the Spitzer Space Telescope or the ATACM, a large millimeter/submillimeter array, ALMA, they see a complex spectrum full of clues, every line a fingerprint of some molecule dancing in the upper layers of this cool, massive star. That same cool temperature has important consequences for mass loss and dust formation. As the star's surface cools, it allows atoms and molecules to condense into dust grains, forming a kind of smoke in the stellar atmosphere. This dust, once formed, is then pushed outward by the star's radiation pressure, forming a slow stellar wind that drifts off into space. This is how red giants like R Doradus slowly disintegrate, shedding their outer envelopes grain by grain, molecule by molecule. It's a delicate, graceful erosion, one enabled by the very coolness of the star's outer layers. Additionally, the low temperature enables detailed observation of stellar opacity, the way light interacts with matter in the star's outer layers. In hotter stars like the Sun, the high temperatures mean the light is dominated by continuous emission and ionized atoms. But in R Doradus, opacity is dominated by molecular absorption, giving rise to strong features in the spectrum that scientists can model to infer temperature, density, and composition. This allows for extremely precise measurements of how the atmosphere behaves over time, how it pulses, loses mass, and evolves. Another fascinating consequence of R Doradus's low surface temperature is its effect on brightness contrast between different parts of the star. In hotter stars, brightness tends to be more uniform across the surface, aside from sunspots. But in cooler, extended atmospheres like that of R Doradus, surface asymmetries become more pronounced. Interferometric observations have revealed that parts of the star's surface are significantly brighter or dimmer than others, indicating either huge convective cells or regions of opacity caused by molecular clouds or dust. These features change with time, contributing to the star's irregular brightness variations and making it a dynamic, evolving object even on short observational timescales. It also means that R Doradus radiates far more infrared than visible light. According to Planck's law, cooler objects emit radiation more efficiently at longer wavelengths. This is why infrared telescopes are key to understanding stars like R Doradus, telescopes that can peer into the cool glow, beyond what human eyes can see. At 2740 K, the peak of its emission lies in the mid-infrared, making it an ideal target for observatories such as Spitzer, ALMA, and the James Webb Space Telescope. From a distance, and to human eyes, R Doradus might seem dim and forgettable. But its cool surface temperature is precisely what makes it unique and valuable to science. It's a window into a different kind of stellar existence, one where low energy per unit area is offset by an enormous surface, where brightness is a function not of heat, but of volume. It's the difference between a bonfire and a smoldering mountain. One dazzles, the other glows with ancient patience. And perhaps most importantly, R Doradus's coolness reminds us of the future. One day, the sun too will cool, swell, and redden. It will no longer shine with the sharp intensity of a yellow star but will transform into a cool red giant, much like R Doradus. When it does, its surface temperature will drop, it will begin to shed its outer layers, and it too will drift toward its final form. In this sense, R Doradus is not just a fascinating subject of observation, it's a mirror held up to our solar system's destiny, a glimpse of the sun's eventual stillness. R Doradus is dying, but not in a way that's sudden or violent. Its demise is slow, deliberate, and atmospheric, marked by one of the most poetic and scientifically rich phenomena in stellar evolution, mass loss. In its current red giant phase, R Doradus is shedding its outer layers into the surrounding space, atom by atom, molecule by molecule. This isn't a cataclysmic explosion, it's more like a constant sigh, a slow, invisible wind, flowing outward in all directions, carrying the star's material into the interstellar medium. This process is known as a stellar wind, but in the case of R Doradus, it's not the kind of high-speed, charged particle wind we observe streaming from the sun. It is instead a cool, dense, and dusty flow, dominated by molecular gas and solid grains. The material that makes up the star's outer atmosphere is so loosely held by gravity, due to the star's immense size and relatively low mass, that it takes very little energy to lift it away. Over time, the outer layers of R Doradus are essentially evaporating into space. The mechanisms behind this gentle shedding are complex but deeply fascinating. As R Doradus pulsates, its massive outer layers expand and cool, creating the perfect environment for dust grain formation. In the cooling gas near the star's surface, molecules condense into tiny solid particles, microscopic grains of silicates, alumina, and metal oxides. These grains absorb radiation from the star and are pushed outward by the momentum of photons. It's a process known as radiation pressure on dust. Because the dust is coupled to the gas, meaning the grains collide with and drag along surrounding molecules, the entire atmosphere is gradually swept away, forming a slow-moving stellar wind that expands into the surrounding interstellar space. These winds travel at a leisurely pace by astronomical standards, typically between 5 to 20 kilometers per second, but they are relentless. Over thousands or millions of years, they will carry away a substantial fraction of the star's original mass. R Doradus is thought to be losing mass at a rate of around 1 times 10 to 1 times 10 solar masses per year. That may not sound like much, but over tens of thousands of years it adds up. To put it into perspective, at the higher end of that range, the star could shed the equivalent of Earth's mass every year. Over time, this results in a huge shell of circumstellar material, an envelope of gas and dust that surrounds the star and reflects, absorbs, and re-emits its light. This is what gives R Doradus its soft, infrared glow and makes it such a prominent object in infrared astronomy. This material is not just drifting aimlessly. It carries with it the raw ingredients for new stars, planets, and life itself. The elements in these winds, carbon, oxygen, silicon, nitrogen, and more, were forged in the heart of the star during nuclear fusion. Now they're being cast back into space, recycled into the galactic ecosystem. When we observe this mass loss, we are watching the beginning of creation, not just the end of a star's life. The structure of this outflow isn't uniform. Observations reveal that the wind is often clumpy, asymmetric, and dynamic. There may be arcs, shells, and irregular blobs of gas moving outward. This complexity likely arises from a combination of factors: pulsations, magnetic fields, convection, and possibly the gravitational influence of a hidden binary companion, if one exists. The interplay between these elements shapes the geometry of the outflow, and may ultimately influence the shape of the planetary nebula that R Doradus will leave behind. We've gained many of these insights thanks to cutting-edge instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, which can detect the molecular gas and dust surrounding stars in exquisite detail. ALMA has revealed the shell-like layers of material around red giants, including R Doradus, showing that each pulsation or outburst may produce a distinct layer of expelled gas, like tree rings marking the star's final centuries. The chemistry of the wind is just as intriguing. In R Doradus's case, its atmosphere contains oxygen-rich molecules, like water vapor, H2O, carbon monoxide, CO, and silicon monoxide, CO. These molecules survive only in relatively cool environments, and their presence helps astronomers understand the temperature gradients and density structure of the outflowing wind. Each molecule absorbs and emits light at specific wavelengths, acting as a probe that scientists can use to map the dynamics of the atmosphere and wind in 3 dimensions. And there's more. Some red giants exhibit dust-driven winds with embedded shocks, miniature sonic booms caused by pulsation waves interacting with atmospheric layers. These shocks can temporarily heat and compress parts of the atmosphere, boosting the wind's speed and altering the formation of molecules and dust. R Doradus, with its semi-regular variability, likely experiences such episodic boosts in wind strength, creating a richly structured and nonlinear mass loss pattern. This process is not only vital for the star's own evolution, but it also sets the stage for its transformation into a white dwarf. As R Doradus loses more and more mass, its outer envelope will eventually become too diffuse to support fusion, and the nuclear reactions that keep the star alive will flicker and cease. What remains will be the exposed core, a hot, dense object made primarily of carbon and oxygen, glowing faintly as a white dwarf. The material expelled during the red giant phase will drift outward, illuminated by the dying core, creating a planetary nebula, a final, beautiful exhalation. So when we look at R Doradus today, we are seeing a star in transition, caught in the act of becoming something else. Its gentle but persistent mass loss is not just a symptom of decline, but an essential stage in the life cycle of stars. It is a sculptor of nebulae, a supplier of interstellar dust, and a bearer of the elements that may one day become part of new solar systems. In the grand cosmic ecosystem, R Doradus is not fading away in isolation, it is feeding the galaxy, breathing out the matter that will seed the next generation of stars and planets. This is not death in the traditional sense. It's stellar metamorphosis, and the mass loss winds are the wings on which this transformation flies. As R Doradus exhales its ancient breath into space, the very material that once composed its fiery body becomes a gift to the cosmos. This act of stellar mass loss isn't a mere shedding of excess weight, it's a foundational contribution to the evolution of galaxies. With every molecule of gas, with every speck of dust blown away by its expanding atmosphere, R Doradus is enriching the interstellar medium, ISM, that vast, diffuse mixture of gas and dust that stretches between stars and becomes the raw material for new celestial structures. This process, while slow and largely invisible to our eyes, is monumental in scope. It is through the death throes of stars like R Doradus that the universe becomes a more chemically complex and fertile place. Early in the universe's history, after the Big Bang, matter was made almost entirely of hydrogen and helium, with only trace amounts of lithium. Heavier elements, what astronomers call metals, including carbon, nitrogen, oxygen, silicon, magnesium, and iron, did not yet exist. These elements had to be forged in the hearts of stars. R Doradus, now in its advanced evolutionary stage on the asymptotic giant branch, AGB, has spent billions of years slowly fusing lighter elements into heavier ones deep within its core and shell layers. The energy generated by these nuclear reactions caused the star to expand into the swollen, cool, and luminous red giant we observe today. But that fusion also created carbon and other heavy elements, the building blocks of life as we know it. Now, as the star loses mass through stellar winds, those fusion products are being released into space. Carbon atoms that were once part of the star's core are now drifting into the interstellar medium. Molecules like carbon monoxide, CO, water vapor, H2O, and silicon monoxide, CO, form in the cooler upper atmosphere, ride the wind, and become part of the diffuse gas between stars. The solid grains of dust, tiny flecks of silicates, alumina, Al2O3, and other oxygen-rich compounds, condense in the cool atmosphere and get swept away by radiation pressure, contributing to the dust reservoirs of the galaxy. This material doesn't just vanish into the void. It accumulates in molecular clouds, cold, dense regions of space where gravity can eventually overcome thermal pressure and trigger the formation of new stars and planetary systems. In this way, the matter from R Doradus will seed future generations of stars. A portion of the atoms from this one ancient giant may one day help light the core of a new sun or become the crust of a new rocky world. Consider this: the carbon in your DNA, the calcium in your bones, the iron in your blood, all of it came from stars like R Doradus. You are, quite literally, made of stardust, and stars like R Doradus are among the most generous contributors of that dust. Without this stellar recycling, the universe would remain chemically primitive, and complex structures, planets, oceans, cells, and minds, would be impossible. Furthermore, red giants like R Doradus create unique types of dust grains and molecules that influence the chemistry of the ISM in profound ways. These dust particles are not just inert debris, they play a crucial role in cooling molecular clouds, acting as catalysts for molecule formation and providing surfaces upon which water and organic molecules can form. They also absorb and scatter starlight, altering the temperature and radiation balance within the ISM and influencing where and how stars can form. This enrichment process also affects galactic evolution on a grand scale. The rate of star formation, the metallicity, i.e., the abundance of heavy elements, of different regions, and even the appearance of a galaxy in different wavelengths all depend on how efficiently stars like R Doradus have enriched the surrounding space. Spiral galaxies, with their rich star-forming arms, rely heavily on materials supplied by dying giants. Elliptical galaxies, less active in star formation, contain older stars and dust that may have originated from similar events billions of years ago. Astronomers have long studied the life cycles of low to intermediate mass stars, like R Doradus, because they dominate the stellar population of the universe. Though not as explosive as massive stars that go supernova, red giants make up for it with sheer numbers and longevity. Over billions of years, they quietly and steadily pollute the galaxy with metals, creating the conditions necessary for complex life to emerge. The contribution from R Doradus and its peers is not just background noise, it is the cosmic baseline for chemical richness and planetary potential. R Doradus's dust is already traveling outward, forming an ever-expanding shell that future astronomers will be able to trace and analyze. The grains will eventually cool and merge with the diffuse galactic environment, losing all signs of their origin. Yet in doing so, they become part of a continuum, part of an ongoing cycle of stellar death and birth that defines the universe's rhythm. One of the most poetic aspects of this process is its long timescale. R Doradus will take thousands, perhaps tens of thousands, of years to shed its outer layers completely. The material it ejects today will take millennia to cool, mix, and collapse into a new generation of stars. From a human perspective, this seems eternal. But from a galactic standpoint, it's a heartbeat. Eventually, once the star has exhausted its mass loss process and all that's left is a dense white dwarf, surrounded by a glowing planetary nebula made of its own discarded atmosphere, the galaxy will have gained not only a beautiful ghostly shell of gas but also a reservoir of elements that could form comets, asteroids, oceans, and brains. When you look at the night sky, the darkness between stars is not empty. It is full of the breath of dying stars, full of dust, carbon, oxygen, everything needed to build worlds. R Doradus is contributing to that cosmic breath, right now, silently and steadily. We are witnessing the act of one star preparing the ingredients for the next cosmic chapter. It is a reminder that even in decline, there is purpose. Even in loss, there is creation. And even in death, there is the beginning of something new. The tale of R Doradus is one of breathtaking grandeur, but like all stories written in the language of stars, it is bound to reach a final chapter. This gentle, pulsing red giant, now glowing in its twilight, is headed toward an ending that is as spectacular as it is transformative, a transformation that will culminate in the formation of a planetary nebula, and the quiet birth of a white dwarf, a stellar ghost containing the final echoes of its former self. As R Doradus continues to lose mass through its powerful, dusty stellar wind, its envelope, the vast, extended atmosphere it has nurtured over millions of years, is slowly being peeled away. With each pulsation, with every molecular puff expelled into space, the star grows lighter. This process is not just a prelude to death, it is the mechanism of rebirth in the broader cosmic sense. When the last layers of gas and dust finally drift away, gravity and pressure will reach a new balance, one that is no longer supported by fusion, but by the quantum pressures of degenerate matter. At the heart of this transition lies the core of R Doradus, which has been gradually accumulating over time as fusion pushed heavier elements inward. This remnant is primarily composed of carbon and oxygen, the ashes of billions of years of fusion. And once the fusion process finally ceases, once the outer hydrogen and helium-burning shells flicker out and can no longer support the star's enormous envelope, this inert core will be exposed. At that moment, the star as we know it will be gone. What remains will be a white dwarf, a dense, Earth-sized stellar remnant composed of matter in a highly degenerate state. White dwarfs do not shine by fusion but rather by residual heat. They are embers, cooling over billions of years. R Doradus's white dwarf will be about half the mass of the Sun, though only a fraction of its original volume. In that form, it will be among the most stable and enduring objects in the universe, destined to shine faintly for trillions of years before fading into cold darkness. But this transformation is not silent. Before the white dwarf emerges in full, the material R Doradus has spent thousands of years ejecting will still be nearby. A massive shell of gas and dust, rich in carbon, oxygen, nitrogen, and complex molecules, drifting just beyond the core. Once the star's internal fusion stops and the gravitational compression of the core begins, the newly born white dwarf will become intensely hot, with surface temperatures exceeding 100,000 Kelvin. It will emit a flood of ultraviolet radiation powerful enough to ionize the surrounding gas, stripping electrons from atoms and causing the ejected shell to glow in stunning, multicolored hues. This glowing shell is what we call a planetary nebula, though the name is misleading. It has nothing to do with planets. The term originates from early telescope observations when such nebulae appeared as small, planet-like disks. In truth, planetary nebulae are beautiful cosmic sculptures, created by dying stars casting off their outer layers in intricate and often asymmetric patterns. The nebula created by R Doradus will not be a perfect sphere. It may take on a shape influenced by many factors: its own pulsations, the complex convective dynamics of its atmosphere, the non-uniform density of the material it expelled, magnetic fields, or even the gravitational tug of a binary companion, if one exists. The result could be a glowing ring, an expanding bubble, or a layered, hourglass-shaped structure adorned with filaments and knots of glowing gas. In this ethereal form, R Doradus will make one final mark upon the galaxy, a brief but spectacular visual echo of a long and complex life. Planetary nebulae are not long-lived on galactic timescales. They typically last for about 10,000 to 20,000 years before the gas disperses into the interstellar medium. But during that time, they shine as some of the most beautiful and scientifically valuable objects in the sky. Through them, we study stellar chemistry, gas dynamics, and the formation of interstellar clouds. Through them, we witness the alchemy of starlight turned into matter. R Doradus's planetary nebula will carry the signature of its history. The composition of the gas will tell us how much carbon and oxygen the star created, how fast it lost mass, and how deeply it dredged material from its interior during thermal pulses. Its structure may hint at hidden asymmetries in the mass loss process, or provide clues to whether a companion helped shape its final breath. And when that nebula finally fades, when the UV light from the white dwarf is no longer strong enough to ionize the gas, the remaining shell will dissolve into the interstellar medium, joining the clouds from which future stars and planets will be born. The white dwarf at the center will cool and dim, eventually becoming a black dwarf, a hypothetical object so cold and inert it can no longer be detected. While black dwarfs are predicted by theory, the universe is not yet old enough for any to exist. White dwarfs remain as timeless markers of stellar legacy. So in R Doradus, we see more than just the fate of a single star. We see the future of our Sun, the exact path it too will follow in 5 to 6 billion years. The Sun will bloat into a red giant, cast off its layers, and eventually leave behind a glowing planetary nebula and a white dwarf core. R Doradus is a cosmic time machine, offering a preview of what lies ahead for our own solar system. There is something poetic, almost sacred, about this finale. A star that has burned for billions of years does not simply vanish. It becomes art, a colorful, luminous sculpture in space. It leaves behind a whisper of light, a final offering to the universe. And it ensures, with every particle it releases, that it will not die in vain. The atoms that once lived in R Doradus's atmosphere will travel the galaxy, become part of other stars, other planets, perhaps even other beings who will look up at the sky and wonder, as we do now. It's one of the most paradoxical truths in observational astronomy. R Doradus, despite being among the largest and most nearby stars in the sky, remains almost entirely invisible to the naked eye. This enormous red giant, which stretches far beyond Mars in hypothetical size and shines brilliantly in the infrared, sits just 200 light-years away, a cosmic stone's throw by galactic standards, yet it goes largely unnoticed by casual stargazers. How can such a behemoth, practically in our neighborhood, elude direct human vision? The answer lies in a blend of astronomical physics, human biology, and geographic circumstance. First and foremost, R Doradus radiates most of its energy in the infrared spectrum, where the human eye is completely blind. Unlike blue or white stars that peak in the visible range, especially at wavelengths our eyes are most sensitive to, R Doradus's light output is concentrated far beyond red, invisible heat rather than visible fire. If our eyes could see infrared, R Doradus would be one of the brightest stars in the night sky. But as it is, we only glimpse the faintest echo of its glow with the unaided eye. Under pristine conditions, extremely dark skies, high elevation, and no light pollution, R Doradus might just barely be detectable to a seasoned observer with perfect vision. Its visual magnitude hovers around plus 5.4 to plus 6.6, depending on its phase of variability, placing it right on the edge of naked eye visibility. But in practical terms, it's rarely, if ever, spotted without optical aid. For most of us, the night sky hides this crimson giant in plain sight. Compounding the challenge is its location in the sky. R Doradus resides in the constellation Dorado, a southern sky constellation that is invisible from much of the northern hemisphere. This constellation lies deep in the southern celestial hemisphere, nestled among stars like Alpha Doradus and Beta Doradus, within a region known for housing the Large Magellanic Cloud, a small satellite galaxy of the Milky Way. But Dorado never rises above the horizon for observers living above approximately 20 degrees north latitude. That means the vast majority of the world's population, especially in Europe, North America, and most of Asia, cannot see R Doradus at all, regardless of optical aid or atmospheric conditions. For observers in the southern hemisphere, R Doradus becomes more accessible, but even then, it rarely commands attention. It doesn't blaze like Sirius, or sparkle like Canopus. Its deep red light, while scientifically significant, is subdued and ghost-like to the human eye. And because it lacks visual brilliance, and sits among a field of more prominent stars and the haze of the Magellanic Clouds, it is often overlooked even by stargazers who know the southern skies well. This elusive nature adds to R Doradus's scientific mystique. Here is a star that ranks among the brightest in the entire sky in the infrared, a superlative, a champion, and yet remains practically invisible without instruments. In fact, it's thanks to the development of infrared astronomy in space-based observatories like Spitzer, Herschel, and now the James Webb Space Telescope that R Doradus has risen in prominence among astrophysicists. These instruments bypass our biological limitations, revealing the star's full glory through sensors that can see what we cannot. In a way, R Doradus represents a kind of astronomical humility check. It reminds us that the universe is not constrained by our perception. What we see with our eyes, what appears bright or colorful, is just a narrow sliver of reality. There are giants among us, hiding behind veils of wavelength and geography, and R Doradus is one of them. The truth is, if we relied solely on visual astronomy, we would completely miss the story of this massive, pulsing, dying star. But once you know where to look, and what tools to use, R Doradus transforms from a faint red speck into a luminary of stellar evolution, a nearby laboratory for understanding red giant stars. Amateur astronomers with moderate-sized telescopes equipped with infrared filters or cameras can detect its presence and track its variability. Observatories with larger aperture scopes can resolve its outer atmosphere and study its complex surface dynamics. In fact, it has become a favored target in stellar interferometry, due to its proximity and size. Despite its faintness in visible light, its enormous angular diameter allows instruments to measure the star's disk directly, making it one of the very few stars, alongside Betelgeuse, Antares, and a handful of others, that we can observe as more than just a point of light. In some ways, this invisibility to the naked eye has preserved R Doradus as a hidden gem, less romanticized by popular astronomy, yet crucial to the advancement of stellar science. Its elusiveness forces us to stretch beyond our sensory limits and develop new ways of seeing the cosmos. And in doing so, we are rewarded with a deeper appreciation for what stars are, how they live, and how they die. So the next time you gaze at the night sky, especially if you're in the southern hemisphere, know that hidden near the fish-shaped boundaries of Dorado, there breathes an invisible titan. R Doradus is not absent, it is merely cloaked in wavelengths our eyes weren't built to detect. But with the right tools, its presence becomes undeniable. It is near, immense, luminous in silence, and all the more awe-inspiring for choosing to whisper rather than shout. Though invisible to our eyes under most conditions, R Doradus is anything but dim. In fact, when viewed not through the narrow lens of visible light, but through the expansive gaze of infrared astronomy, R Doradus emerges as one of the most brilliant non-solar objects in the entire sky. Its unassuming presence in the visible spectrum masks its dominance in the infrared, where it consistently ranks among the brightest stellar sources ever recorded, second only to a few celestial heavyweights like Betelgeuse or Mira in specific infrared bands. In some wavelengths, it even outshines them all. The reason behind this brightness lies in the nature of blackbody radiation and how stars like R Doradus emit energy. With a surface temperature of approximately 2740 Kelvin, R Doradus sits on the cool end of the stellar spectrum. According to Planck's law, cooler objects radiate more intensely in longer wavelengths, particularly in the mid and far infrared. The peak of R Doradus's electromagnetic emission isn't in the visible light that our eyes can detect. It lies deep in the infrared region, invisible to unaided observers but radiating powerfully to instruments designed to sense heat and long-wave light. Because of its immense size and surface area, the star compensates for its lower temperature by emitting sheer quantities of infrared radiation. Every square meter of its surface radiates less than the sun's, but it has so many more square meters, hundreds of millions more, that its total infrared output becomes staggering. This is why, when telescopes like the Spitzer Space Telescope, Infrared Astronomical Satellite, IRAS, ACARI, or the James Webb Space Telescope, JWST, scan the sky in these wavelengths, R Doradus appears as a brilliant source, a red giant lighthouse in the dark. Its infrared brightness has made R Doradus an essential calibration target for many infrared missions. Because it is relatively stable in its output over long timescales, despite its slow, semi-regular pulsations, it offers a consistent benchmark for calibrating instruments and verifying the sensitivity of detectors. These missions often need standard candles, in the infrared, objects that are reliably bright and well understood. R Doradus, with its large, predictable infrared signature, fits this role perfectly. But its dominance isn't just a tool for other observations, it also reveals critical insights about stellar structure, composition, and evolution. Infrared light penetrates dusty environments far more effectively than visible light. This means astronomers can peer into the circumstellar envelope of R Doradus, the layers of gas and dust that it has ejected into space, without being blinded or blocked by the material itself. Infrared observations reveal the temperature gradients, density fluctuations, and composition of this envelope with astonishing clarity. For instance, infrared spectroscopy has uncovered rich molecular fingerprints in the light of R Doradus, lines from water vapor, carbon monoxide, silicon monoxide, and metal oxides that absorb and emit radiation at characteristic wavelengths. These molecules are not only evidence of the star's cool outer atmosphere, but also of the complex chemistry that red giants produce before they die. Understanding how these molecules form, evolve, and interact with the radiation field helps scientists build models of mass loss, dust formation, and wind acceleration in late-stage stellar evolution. One particularly fascinating application of its infrared brilliance comes in the field of stellar interferometry. Interferometers combine the light from multiple telescopes to create effectively a single, enormous telescope with extremely high resolution. Because R Doradus is so large in angular diameter and so bright in the infrared, it is a prime target for resolving its actual surface structure, not just measuring its brightness, but seeing how that brightness varies across its disk. This has allowed astronomers to detect giant convective cells, hot spots, and asymmetries in the star's atmosphere, features that would be impossible to discern without its infrared dominance. Moreover, its brightness in these wavelengths also makes R Doradus a foreground object in many extragalactic surveys. For example, missions targeting the Large Magellanic Cloud, which lies in the same region of the sky as Dorado, must carefully account for the infrared glow of R Doradus to avoid contamination in their data. This foreground brilliance is so pronounced that in low-resolution images, R Doradus can create bright streaks, saturation artifacts, or blooming effects, depending on the sensitivity of the detectors. It's like trying to photograph a dim candle in a room while a bonfire blazes nearby. R Doradus overwhelms everything around it. In recent years, the James Webb Space Telescope has offered an unprecedented opportunity to revisit R Doradus with new eyes. With its exquisite sensitivity and resolution in the mid-infrared, JWST has begun to resolve not only the structure of the star's atmosphere but also the morphology of the surrounding dust shell, a cocoon of expelled material that glows with thermal radiation. These observations can detect spiral arms, rings, or arcs within the dust, potentially revealing the gravitational influence of a binary companion, or episodic changes in mass loss associated with the star's pulsation cycle. The depth of data gathered from R Doradus's infrared light also feeds directly into broader models of stellar population synthesis, the process by which astronomers simulate the makeup of entire galaxies. By studying R Doradus and stars like it in the infrared, scientists can refine their models of how stars age, how they die, and how their contributions of dust and gas shape the spectral energy distributions of galaxies seen across cosmic time. Red giants dominate the infrared output of older stellar populations. Thus, understanding the behavior of stars like R Doradus is key to interpreting the light from distant galaxies billions of light-years away. So while R Doradus may pass unnoticed in a night sky full of flashier visual stars, it is in the infrared where its true identity shines through, a beacon for astronomers, a laboratory of dying starlight, and a reminder that the cosmos is always more vibrant than what our eyes alone can perceive. It is a giant not in stature alone, but in influence, casting a quiet but brilliant light on the pathways of stellar death, chemical creation, and galactic evolution. To miss R Doradus in the visual sky is to miss a ghost. But to capture it in the infrared is to witness a titan, glowing with a kind of cosmic dignity that few stars can match. Surrounding the vast, pulsating body of R Doradus is a delicate shroud, a dusty cocoon, ethereal and expanding, born from the star's own breath. This envelope of cosmic debris is not merely an incidental byproduct of its dying phase. It is a signature feature of what R Doradus has become in its final act, a star steadily peeling itself apart, atom by atom, into the emptiness of space. As R Doradus swells and cools in its red giant state, its outer layers become increasingly unstable and gravitationally unbound. In these expanded atmospheric layers, where the temperature has dropped enough for atoms to begin bonding, dust grains begin to form. These grains, microscopic particles of silicates, alumina, Al2O3, and oxides of iron, magnesium, and calcium, condense out of the cooling gas like frost on a windowpane. The conditions here are perfect for such creation: low temperatures, high densities, and rich chemistry, all swirling in slow, dynamic motion. Radiation from the star's interior, particularly infrared radiation, exerts pressure on these dust grains, pushing them outward. Since these grains are intermingled with the gas in the atmosphere, they drag gas molecules along with them, forming what is known as a dust-driven stellar wind. This is not a violent outburst, like a supernova, but a steady, continuous outflow. Over thousands of years, this outflow has accumulated to form a massive, dusty shell around the star, extending over vast distances. This shell is semi-transparent, glowing faintly in the infrared as it re-emits the energy it absorbs from the star. It creates a thermal halo around R Doradus, observable in infrared wavelengths, rendering it even more luminous in that spectrum. Infrared images of the star reveal a soft, extended glow rather than a pinpoint, indicating that we're not just seeing the star itself, but also its expanding envelope of dust. And this dust is not smooth or uniform. Observations, especially those using the Atacama Large Millimeter/Submillimeter Array, ALMA, and other interferometric techniques, show that the dust shell around R Doradus is clumpy, asymmetric, and structured. There are denser regions where dust has built up, likely corresponding to specific pulses or ejections of material. These may form arcs, shells, or even spirals if the star has a companion that influences the geometry of its outflows. Some parts of the shell appear brighter and more defined, while others fade into the background, suggesting a non-uniform history of mass loss. This structure offers rich clues into the internal dynamics of R Doradus. It reflects the timing and strength of its pulsations, the presence of magnetic fields, and even the star's own rotational behavior. The dust doesn't just form and float away, it carries an imprint of the stellar processes within. In this way, the shell becomes both a relic and a record, a kind of cosmic fossil documenting the end-of-life heartbeat of a star. In addition to being visually compelling, the dust shell around R Doradus plays a vital physical role in the broader galactic environment. Dust grains serve as the seeds for molecular cloud formation, providing surfaces upon which molecules like water, H2O, carbon monoxide, CO, and even complex organics can form. These grains cool the surrounding medium, enabling gas clouds to collapse more easily under gravity, facilitating the birth of new stars and planetary systems. Moreover, this dust influences the light we see from R Doradus and its surroundings. The grains scatter, absorb, and re-emit radiation, altering the star's apparent brightness, color, and spectrum. To accurately interpret observations of R Doradus, astronomers must account for the effects of this shell. It dims the star's visible light while enhancing its infrared glow, and it can even polarize the light it scatters, offering another diagnostic tool for understanding the shell's composition and geometry. Studies suggest that the dust production rate for R Doradus is significant, though lower than that of more extreme mirror-type stars. Its semi-regular variability results in a steadier but somewhat more modest ejection of material. However, because of the star's proximity, just 200 light-years away, its dust shell is easier to study in fine detail than most. We can track the motion of individual dust clumps, observe changes in brightness over time, and model how radiation and matter interact in real time. This level of observational access has made R Doradus a template for understanding dust formation and wind dynamics in similar stars across the galaxy. By watching how its dusty shell evolves, astronomers can extrapolate to more distant, less accessible red giants, piecing together a larger story of how stars contribute to the chemical and structural evolution of the Milky Way. And there's something profoundly poetic about it. This once vigorous star, now nearing the end of its life, creates beauty not in fire and flame, but in dust and breath. It doesn't erupt, it exhales, coating the space around it in grains that may one day settle into new suns, new planets, or perhaps even the building blocks of life. The dusty shell of R Doradus is not a coffin, it is a chrysalis, the transitional stage between what the star was and what its matter will become. It marks not an end, but a transformation, an alchemical moment when aging light becomes the raw material of the future. The atmosphere of R Doradus is not merely a featureless, glowing plasma, it is a complex, chemically rich environment, teeming with molecules that should, by many intuitive standards, not exist in the harsh realms of a stellar surface. And yet, in the delicate, extended layers of this red giant's swollen outer envelope, molecules such as water vapor, H2O, carbon monoxide, CO, silicon monoxide, CO, and metal oxides like titanium oxide, TiO, not only exist, they thrive. Their presence is both scientifically invaluable and astronomically rare, turning R Doradus into a kind of stellar chemistry laboratory, uniquely accessible due to its proximity and infrared brilliance. In hotter stars like the Sun, temperatures are so extreme, averaging around 5,800 Kelvin, that atoms are ionized, molecular bonds are ripped apart, and the stellar photosphere is a seething sea of unbound particles. But in red giants like R Doradus, whose surface temperature hovers around a comparatively cool 2,740 Kelvin, conditions in the upper atmosphere become gentler. This reduction in thermal violence allows molecules to form and remain stable for significant periods. At first glance, the idea of water vapor existing on a star might seem absurd. After all, stars are synonymous with heat, and we typically associate water with much cooler planetary environments. But within the cool, extended layers of R Doradus, far above the visible photosphere, there exist regions where the temperature and pressure drop low enough for hydrogen and oxygen to bond into water molecules. These molecules absorb and emit light in the infrared region, leaving distinct fingerprints in the star's spectrum. This discovery was made possible through infrared spectroscopy, a technique that analyzes the light emitted or absorbed by molecules at different wavelengths. The absorption lines associated with water, carbon monoxide, and other molecules are extremely specific, like barcodes for each compound. Observations from space-based telescopes like Spitzer and ISO, Infrared Space Observatory, along with high-resolution ground-based facilities such as ALMA and VLT, Very Large Telescope, have confirmed the presence of these molecules in our Doradus's atmosphere. Carbon monoxide, CO, in particular, is abundant and incredibly important. CO forms very efficiently wherever carbon and oxygen coexist, and because it is chemically stable and radiatively active, it plays a key role in regulating the thermal structure of the stellar atmosphere. It effectively acts as a thermostat, absorbing excess heat and redistributing energy. Its spectral lines are also excellent tracers of gas velocity and turbulence, allowing astronomers to measure how fast material is moving in and out of the star's outer layers. Silicon monoxide, CO, is another intriguing molecular player. It contributes not only to the gas phase chemistry but also serves as a seed for dust formation, condensing into solid grains that form part of the dusty wind enveloping the star. Observing the emission lines of CO masers, amplified microwave emissions created in very specific atmospheric conditions, has enabled scientists to map the motion of gas clouds just above the photosphere of our Doradus in remarkable detail. These masers can reveal oscillations, shock waves from pulsations, and even asymmetries caused by local convective cells or magnetic fields. What makes this molecular menagerie so fascinating is not just the chemistry itself, but what it tells us about the physical structure of the star. The existence of molecules implies that our Doradus has a layered, dynamic atmosphere, with temperature gradients, pressure zones, and regions of high and low density. These layers are constantly in motion, stirred by pulsations, convection, and radiation pressure, creating a chaotic but coherent dance of matter and light. Additionally, the chemistry offers crucial insight into the evolutionary phase of the star. Molecules like water and CO are far more prevalent in stars that have passed the red giant branch and moved on to the asymptotic giant branch, AGB, a phase characterized by double shell burning and intense mass loss. Their detection confirms that our Doradus is nearing the end of its stellar life, actively shedding its atmosphere and preparing to leave behind a planetary nebula. There's also an astrobiological fascination with these molecular discoveries. While no life can exist in or near a star, the chemical pathways that produce water, carbon compounds, and complex molecules are the very same that, in colder environments, might lead to organic chemistry and prebiotic conditions. The molecules expelled by our Doradus will eventually cool and settle into the interstellar medium, where they might become part of planet-forming clouds, perhaps even ones capable of giving rise to life-bearing worlds. Beyond their scientific utility, there's something viscerally poetic about molecules like water vapor, so central to our existence, forming in the atmosphere of a dying star. It's as if the elements that sustain life on Earth are returning to the stars that forged them, creating a kind of cosmic echo, a chemical déjà vu that spans light years and eons. And because our Doradus is so close and so bright in the infrared, it provides a rare opportunity to observe these molecules not just as lines in a spectrum, but as active agents in stellar evolution. We can track how they form, how they move, how they react to the pulses of the star, and how they influence the formation of dust and the structure of the outflowing wind. Molecules are ephemeral by nature, but in our Doradus, they become witnesses to cosmic time, telling us not only what the star is made of, but what it is doing, where it has been, and where it is going. They are more than chemistry, they are narrators, speaking in the silent frequencies of infrared light, helping us read the last chapters of a star's biography. To understand a star as vast, complex, and enigmatic as our Doradus, we must reach beyond the limits of human vision, and even beyond the capabilities of traditional telescopes. That's exactly what astronomers have done in recent decades, drawing upon some of the most powerful observatories ever built to study this nearby red giant in unprecedented detail. Among them, two stand out for their transformative contributions: the Atacama Large Millimeter/Submillimeter Array, ALMA, and the now retired but still scientifically vital Spitzer Space Telescope. These instruments, working in wavelengths invisible to the human eye, have opened a window into the living, breathing atmosphere of R Doradus and the dusty environment that surrounds it. Let's begin with ALMA, perched high in Chile's Atacama Desert. Operating at millimeter and submillimeter wavelengths, ALMA is exquisitely tuned to detect cold gas, molecular clouds, and thermal radiation from dust, exactly the types of emissions that R Doradus produces in abundance. Because it is composed of 66 individual radio dishes, ALMA uses interferometry to combine the data from these antennas into a single high-resolution image, with a clarity akin to that of a telescope several kilometers wide. This level of detail has proven revolutionary for red giant studies, and R Doradus has been a major beneficiary. ALMA has been able to resolve the extended atmosphere and surrounding gas envelope of R Doradus, detecting molecular species like carbon monoxide, CO, silicon monoxide, CO, and even water vapor. These observations aren't just about composition, they reveal the velocity, direction, and turbulence of gas flows, essentially allowing scientists to watch R Doradus exhale, layer by layer. One of the most striking findings from ALMA's data was the irregularity and clumpiness of R Doradus's stellar wind. Instead of a smooth, spherical outflow, the gas appears in pockets and arcs, with regions of higher density indicating episodic or localized mass ejections. This hints at the presence of giant convective cells or thermal pulses that shake the star from the inside out. In some cases, the data even suggests spiral structures, which could be the gravitational imprint of a hidden binary companion orbiting R Doradus, a tantalizing possibility still under investigation. Moreover, ALMA's ability to capture Doppler shifts in the spectral lines lets astronomers map how gas is moving, toward us or away from us, with precision. This enables the construction of three-dimensional models of R Doradus's circumstellar environment. It's no exaggeration to say that ALMA has transformed R Doradus from a faint point of infrared light into a complex, dynamic structure, one whose every breath and pulse is becoming clearer to us. Meanwhile, the Spitzer Space Telescope, which operated from 2003 to 2020, brought its own unique capabilities to bear. Spitzer was designed specifically to observe the infrared universe, and for stars like R Doradus, whose peak emission lies in this range, it was nothing short of revelatory. Spitzer provided high-resolution infrared spectra and images, revealing the temperature, density, and chemical composition of both the star and its extended dust shell. Spitzer confirmed that R Doradus was one of the brightest mid-infrared sources in the sky, and its photometric measurements helped calibrate stellar models used across infrared astronomy. Its instruments detected thermal emission from silicate and alumina dust, measured the thickness of the circumstellar shell, and even observed changes in brightness over time, corresponding to the star's pulsation cycle. In this way, Spitzer served as both a light meter and a chemical probe, helping to construct a full portrait of the star's atmosphere and the dust-rich wind it generates. Together, Spitzer and ALMA provided a complementary perspective. Spitzer captured the broad strokes, the light, the heat, the overall profile, while ALMA zoomed in on the fine details of molecular motion and gas dynamics. Thanks to these missions, astronomers could finally begin answering deep questions about stars like R Doradus. How does mass loss begin? What role do molecules play in dust formation? How does stellar pulsation influence atmospheric chemistry? And could a companion star be shaping the outflow into complex patterns? The knowledge gained from these observatories also feeds directly into the next generation of stellar models. By comparing observational data with theoretical simulations, astrophysicists are refining our understanding of asymptotic giant branch, AGB, evolution, dust-driven winds, and the preplanetary nebula phase. R Doradus serves as a case study, a nearby, relatively uncomplicated red giant that allows scientists to test their predictions with real, high-fidelity data. But the story doesn't end with Spitzer and ALMA. Other powerful observatories have contributed as well. The Very Large Telescope, VLT, in Chile has used adaptive optics and interferometry to study the surface features of R Doradus, revealing brightness variations and suggesting the presence of giant convective cells. The Herschel Space Observatory, now decommissioned, detected far-infrared and sub-millimeter emissions from the outermost parts of the dust shell. And most recently, the James Webb Space Telescope, JWST, is expected to revisit R Doradus with even greater clarity, pushing the boundaries of what we can detect and measure in such a nearby, evolved star. Each of these telescopes, in their own way, has helped transform R Doradus from an obscure infrared source to a cornerstone of stellar astrophysics. No longer just a dot in the southern sky, it is now a well-mapped, multidimensional object, studied in dozens of wavelengths and under the scrutiny of the finest instruments humanity has ever devised. There is something profoundly satisfying in this transformation. A star that once lay hidden by the veil of invisibility, not due to distance or obscurity, but simply because it shone in light our eyes cannot see, has become one of the best understood red giants in our galactic neighborhood. It's a testament not only to the power of modern astronomy, but to the persistent curiosity of those who build machines to capture the invisible, decode the distant, and uncover the quiet beauty of the dying stars around us. R Doradus, at first glance, might appear, like most stars, to be a nearly perfect sphere, round, radiant, and symmetrical. But delve deeper with the extraordinary technique of stellar interferometry, and that illusion quickly dissolves. What we find instead is a star whose outer layers are far from uniform, an immense celestial body whose surface ripples, warps, and bulges under the weight of internal forces and ancient rhythms. With the help of interferometry, astronomers have discovered that R Doradus is not a smooth ball of fire, but a living, breathing object, textured by convection, pulsation, and dynamic winds. Unlike traditional telescopes, which are limited in their resolution by the size of their primary mirrors, stellar interferometry combines the light from multiple telescopes spread over vast distances to create an instrument with the resolving power of a much larger one. In the case of arrays like the Very Large Telescope Interferometer, VLTI, in Chile or the Chara Array in California, the effective telescope diameter can be hundreds of meters. This allows for unprecedented spatial resolution, enough to actually resolve the disks of nearby stars, something typically impossible for all but the very largest and closest stars. R Doradus, thanks to its immense angular diameter, among the largest of any star in the sky, has been a perfect candidate for this technique. While most stars appear as unresolved points even in the most powerful optical telescopes, R Doradus is so large and so near that interferometry can actually image the star's surface, revealing its shape, brightness variations, and even surface features. The results have been astonishing. Instead of a clean, spherical outline, R Doradus presents a distorted, lopsided profile. Its outer atmosphere is irregular, with brightness hotspots, dimmer regions, and uneven extensions. Some parts of the star appear to bulge outward, while others seem more recessed, almost like a slow-motion wave rolling across its surface. These distortions are not random. They are the visible consequences of the star's pulsation cycles and massive convective currents within its outer layers. One of the most significant revelations is the detection of giant convective cells, far larger than anything seen on the Sun. These are upwelling regions of hot gas, rising from deep within the star and breaking through the surface layers before cooling and sinking back down. On the Sun, these appear as granules about 1,000 kilometers wide. On R Doradus, each of these convective cells could be as large as the Earth or even larger, spanning tens of millions of kilometers. They shift and evolve slowly over time, creating asymmetrical brightness patterns across the star's disk. Interferometric images have also revealed temperature variations across the surface. Some regions are hotter, radiating more light. Others are cooler, often corresponding to the presence of stellar, star spots, massive magnetic disturbances that temporarily suppress convection. These spots aren't quite like sunspots, but they share a similar principle. The combination of convective cell dynamics, magnetic activity, and pulsation-induced expansion and contraction creates a complex, evolving surface geometry. Even more intriguing is that the star's apparent shape fluctuates over time. As R Doradus pulsates, over its roughly 332-day cycle, it doesn't simply grow and shrink uniformly. Instead, the expansion may be slightly stronger in some regions than others, leading to an aspherical inflation of the stellar atmosphere. This creates a kind of wobble in the star's shape, and interferometric studies have caught R Doradus in various stages of these undulations. It appears to expand more along certain axes at particular times, giving it an ellipsoidal appearance, though not one that remains constant. The presence of asymmetry in the outer layers has important implications. It means that mass loss from R Doradus is also likely asymmetric, with certain directions seeing stronger outflows. This could explain the irregular structure of the surrounding dust shell, with denser clumps and arcs appearing more prominently in one hemisphere than the other. It also raises the possibility that internal magnetic fields, twisting and interacting with the star's rotation and convective flows, are playing a hidden but crucial role in shaping the star's end-of-life dynamics. Moreover, these surface distortions challenge the simplistic models of stellar evolution that assume spherical symmetry. In order to truly understand stars like R Doradus, astrophysicists must now construct three-dimensional, time-variable models that account for convective turbulence, magnetic fields, rotational dynamics, and the feedback between pulsation and mass loss. This is a computationally intensive challenge, but thanks to the constraints provided by interferometric data, these models can be grounded in real, observable phenomena. There's also the possibility that some of the observed asymmetries could be influenced by an unseen companion star. If R Doradus is part of a binary system, the gravitational tug of its partner could distort its outer atmosphere, pulling it slightly out of round and channeling gas preferentially along the orbital axis. Interferometric imaging has yet to conclusively detect such a companion, but subtle deviations in the star's shape and surrounding dust might be pointing to its presence. Ultimately, interferometry doesn't just provide a picture, it provides motion, structure, and variability. It transforms R Doradus from a dot into a dynamic sphere, one whose skin is rippling with activity, whose breath pulses in and out, and whose shape changes with time. It is a star rendered not as an idealized model, but as a real, complex object, subject to the same kinds of imperfections and irregularities that define so much of the natural universe. And from a poetic standpoint, there is something deeply moving about this. We often think of stars as perfect, eternal, geometric lights in the sky. But here is R Doradus, lopsided, uneven, constantly shifting, a reminder that even the grandest entities in the cosmos are subject to the same principles of chaos and change that govern life itself. It is imperfect, beautifully, profoundly so. And thanks to stellar interferometry, we get to witness that imperfection in exquisite, glorious detail. When we speak of weather, we usually imagine Earth's dynamic skies, storms swirling in the atmosphere, clouds drifting, and winds reshaping the environment. But R Doradus, a distant red giant star nearly 200 light-years away, has its own form of weather, a cosmic-scale meteorology that plays out not in air, but in boiling plasma, gigantic convection currents, and massive star spots. This star's surface is not a static, glowing shell, it is a restless, ever-changing environment sculpted by forces far more powerful than any earthly storm. At its immense size, more than 350 times the diameter of the Sun, R Doradus's outer layers behave very differently from those of a smaller, more compact star. Its gravity at the surface is comparatively weak, allowing gas to float, rise, and fall with far greater freedom. These conditions give rise to giant convective cells, immense, churning zones of plasma that rise from deep within the star's interior and radiate outward, only to cool and descend again in slow, enormous cycles. On the Sun, convection happens in cells called granules, each about the size of Texas, visible as tiny bright spots and dark boundaries across the photosphere. But R Doradus is a different beast altogether. With its low gravity and cooler surface temperature, each of its convective cells can span up to 20 to 30% of the star's visible surface. We're talking about structures the size of entire planets, evolving and shifting over weeks and months. Rather than having millions of small granules like the Sun, R Doradus likely has just a few dozen of these gigantic cells at any given time. And each one leaves a noticeable mark on the star's brightness and shape. These cells create surface irregularities, regions that are brighter or darker depending on whether hot material is rising or cooler plasma is falling. Interferometric imaging and infrared light curves have provided the evidence. R Doradus's brightness varies not just in time, due to pulsation, but also across its surface. These brightness variations are interpreted as signs of surface weather, caused by the slow turnover of giant convective cells. Imagine, then, what this would look like if you could hover above the star. One region, glowing brighter than the rest, might be the hot, bubbling crest of a convective upwelling, like magma rising from deep within the Earth. Nearby, a cooler, dimmer region might signal a descending plume of gas, gradually sinking back into the deeper layers of the star. The entire surface would seem to writhe and pulse, not from light alone, but from the internal circulation of the star's body. But there's more. In addition to these convective cells, R Doradus may also host star spots, regions of localized magnetic activity where convection is temporarily suppressed. These spots can appear darker in the infrared or visible light and may last for months or even years. While sunspots on our own star are relatively modest in size, those on R Doradus, if they exist, could be thousands of times larger, encompassing vast swaths of the stellar surface. These are not little blemishes. They are monumental scars, created by tangled magnetic fields emerging from the star's interior. Magnetism in red giants is still a subject of active research. While red giants like R Doradus rotate very slowly, suggesting less magnetic dynamo action compared to faster rotating stars, their massive convective zones and pulsation may still allow for localized magnetic field generation. Observations of polarized light and subtle spectral changes support the idea that R Doradus could harbor a weak, but active magnetic field, capable of producing star spots or even magnetic loops like those seen on the Sun. When you combine all these effects, convective cell turnover, spot formation, and ongoing pulsation, you get a star whose outer surface is in constant flux, sculpted by deep internal rhythms and forces. It's a kind of stellar weather system, with no atmosphere as we understand it, but with turbulence and energy flows on a scale that's hard to fully comprehend. The light that reaches us, filtered through this roiling layer, is therefore not steady, but subtly modulated, sometimes brighter, sometimes dimmer, and always hinting at complex motion beneath the surface. This weather is more than a curiosity. It has practical consequences for our observations. For instance, the surface asymmetry caused by these convective patterns affects how we measure the star's diameter, its luminosity, and even its apparent motion across the sky. Changes in brightness due to a rotating convective cell or a star spot can be mistaken for other phenomena if not properly accounted for. As a result, scientists must build detailed models of stellar atmospheres that incorporate convection, radiative transfer, and magnetic activity, just to decode what they're seeing. Additionally, the star's weather likely plays a crucial role in mass loss. The convective cells, by pushing gas upward, bring material closer to the escape velocity threshold. Combined with radiation pressure and pulsation, this can facilitate the outflow of gas into space. In this way, the surface weather is not just a surface detail, it's part of the engine that drives the star's eventual demise. Astronomers are now turning to next-generation instruments, like the James Webb Space Telescope, JWST, and upcoming ground-based interferometers, to track this weather in real time. Observing R Doradus over days, weeks, and years, we may one day watch individual cells form, evolve, and fade. We might see star spots drift across its face or observe how magnetic fields redirect mass loss. This is not idle speculation, it is an unfolding reality, made possible by our rapidly advancing ability to observe stars as multidimensional, dynamic worlds. There is something profoundly humbling in this. From nearly 200 light-years away, we are watching the surface of a star move, shift, and change, not as myth or metaphor, but as literal motion. The cosmic weather of R Doradus is an eloquent reminder that stars are not static furnaces, burning in silence, but vast, living machines, hot, turbulent, and ever-changing. As we peer more deeply into the turbulent, luminous life of R Doradus, one mystery continues to linger, quietly pulling at the edges of scientific curiosity. Is it truly alone? Despite its seemingly solitary existence in the southern sky, there is growing evidence, though still inconclusive, that R Doradus may, in fact, have a hidden stellar companion orbiting nearby. If proven true, such a discovery could help explain several puzzling features of the star's behavior, from its asymmetric mass loss to the unusual structure of its surrounding dust shell. Binary systems are far more common than most people realize. In fact, the majority of stars in the Milky Way, particularly massive or evolved stars, are part of binary or multiple star systems. These stellar partnerships can influence everything from rotational speed and magnetic activity to the way mass is transferred, lost, or even stolen between companions. In some cases, a companion star can remain hidden for centuries, concealed by its brightness difference, or its close proximity to the larger star's blinding glare. In the case of R Doradus, no obvious visual companion has been directly observed, at least not one bright enough to stand out clearly in conventional imaging. Yet, a series of indirect clues have led astronomers to suspect that a fainter, compact, or lower mass companion might be present, tugging gently at R Doradus in ways we can only detect through careful analysis. One of the first signs pointing toward a potential companion comes from the asymmetry observed in R Doradus's circumstellar environment. When imaged in the infrared or radio wavelengths, the dust shell around R Doradus does not appear perfectly spherical. Instead, it displays density enhancements, arcs, and even hints of spiral-like structures, patterns that, in other evolved stars, have been attributed to the gravitational sculpting of a binary companion. In binary systems, material lost from the red giant can form a spiral shell due to the orbital motion of both stars. If R Doradus exhibits similar features, it could very well be a signpost of an unseen partner. In addition, some studies using stellar interferometry have suggested slight deviations in the motion of the star's center of mass, as well as irregularities in its light curve that do not correspond neatly to its known pulsation period. These wobbles might be caused by the gravitational influence of a smaller object orbiting R Doradus, perhaps a low-mass red dwarf, a white dwarf, or even a brown dwarf, too dim to be seen directly but massive enough to leave an imprint on the star's motion. To investigate this possibility further, astronomers have turned to radial velocity measurements, the method used so successfully in the hunt for exoplanets. By carefully measuring the Doppler shifts in the spectral lines of R Doradus, scientists can detect tiny oscillations in the star's motion toward and away from Earth. While challenging due to the pulsations and atmospheric variability of red giants, this technique has proven effective in spotting companions around other evolved stars. The results so far have been intriguing but inconclusive. Some observations hint at periodic velocity shifts that could suggest an orbiting body, but these shifts are often confounded by the star's internal pulsation and convection patterns, which can mimic orbital motion. In effect, R Doradus is so dynamic, its surface rising and falling like a slow tide, that teasing out the subtle gravitational wobble of a companion becomes a complex and uncertain task. Another avenue of inquiry comes from astrometric data, particularly from the European Space Agency's Gaia mission, which is measuring the precise positions and motions of over 1 billion stars. As Gaia continues to refine its data set, even the slightest perturbations in the motion of stars like R Doradus could reveal the presence of companions. If R Doradus's path through space exhibits a gentle sway, a sign of being gravitationally tethered to another object, Gaia may one day confirm it. A companion, if it exists, would profoundly alter our understanding of how R Doradus evolves. In binary systems, mass transfer events are common. The red giant may lose mass not just into the void, but toward its partner, creating accretion disks or even triggering nova-like phenomena in more compact companions. A close binary could explain why some material appears to be ejected asymmetrically, or why the dust shell is denser along certain axes. In the long term, a companion could influence when and how R Doradus sheds its outer layers and transitions into a planetary nebula and white dwarf. Even more tantalizing is the idea that the companion could be a white dwarf, the leftover core of a once massive star that evolved earlier than R Doradus. In such a scenario, the two stars may have formed together, but the smaller one lived fast and died young, leaving behind a dense, faint remnant. If R Doradus is currently transferring mass to this white dwarf, it could eventually trigger a symbiotic outburst, a temporary brightening caused by the accumulation and ignition of material on the companion's surface. As of now, the existence of a companion star remains one of the most fascinating open questions in the study of R Doradus. It's a classic astronomical whodunit. We see the effects, dust spirals, asymmetries, gravitational hints, but not the culprit itself. Continued observation, particularly with high-precision instruments like ALMA, Gaia, and the James Webb Space Telescope, will be key to solving the mystery. In a broader sense, this ongoing search speaks to the layered complexity of stellar lives. What appears at first to be a solitary giant may in fact be part of a quiet, intricate partnership, one that has shaped its evolution from the beginning, and may still be guiding its final breaths. If R Doradus does indeed have a companion, then its story is not just that of one star fading, but of two stars dancing, sometimes seen, sometimes hidden, across the deep time of the cosmos. To look at R Doradus is, in many ways, to look ahead into the distant future of our own sun, a kind of cosmic time machine offering a preview of what lies in store, not just for the center of our solar system, but for everything that orbits it. Though the sun is far younger and less evolved, the path it follows is already written in the physics of stellar evolution, and R Doradus, a massive, bloated red giant in the final chapters of its life, serves as a luminous example of what happens when a once stable star exhausts its fuel, loses its grip on its outer layers, and begins its slow, dramatic transformation into something completely different. Let's begin with the key parallel. Both R Doradus and the Sun are low to intermediate mass stars. While their current appearances differ drastically, they are kin in terms of mass and basic stellar structure. This makes R Doradus an excellent analog for what our Sun will one day become. The Sun is now about 4.6 billion years old, roughly halfway through its main sequence life. During this stable period, it fuses hydrogen into helium in its core, producing the heat and light that sustains life on Earth. But this balance cannot last forever. In roughly 5 to 6 billion years, the hydrogen in the Sun's core will become depleted. When that happens, the core will contract under gravity, and the outer layers will expand dramatically. The Sun will swell into a red giant, growing to dozens, then potentially over 100 times its current size. Its surface will cool, and it will take on a deep, ruddy hue, just as R Doradus does today. In this phase, the Sun will leave behind the placid, life-giving behavior we know and become a volatile, fluctuating giant. R Doradus offers a vivid depiction of that future. Its bloated, loosely held outer atmosphere, its cool surface temperature of around 2740 K, and its pulsing brightness are all signs of a star nearing the end of its stable existence. This is a star that has moved beyond the red giant branch and is now ascending the asymptotic giant branch, AGB, a stage that our Sun will also eventually reach. In this state, helium and hydrogen are fusing in shells around an inert core, creating intense energy fluctuations and driving powerful stellar winds. Our Sun, too, will someday enter this advanced red giant phase. When it does, its diameter will swell to possibly engulf Mercury, Venus, and perhaps even Earth. While this doesn't mean the planet will be swallowed in a clean gulp, the boundary of a red giant is diffuse, not a hard surface. It does mean Earth will be scorched, its oceans boiled away, and its atmosphere lost to space long before it touches the star itself. Life as we know it will not survive this transformation. But just as R Doradus now sheds its outer layers in a dusty, molecule-rich wind, so too will the Sun begin to peel away its atmosphere, particle by particle, molecule by molecule, over hundreds of thousands of years. The gas and dust ejected during this stage will be enriched with the elements created by fusion, carbon, nitrogen, oxygen, and other heavy elements, and will eventually become part of the interstellar medium, helping to form new stars, new planets, and potentially, new life elsewhere. This process is part of a grand cosmic cycle. Stars like the Sun and R Doradus are element factories, creating the raw materials of life and dispersing them into the galaxy. Without red giants, there would be no carbon-based life, no rocky planets, no oxygen to breathe. In this way, R Doradus is not only a warning of the Sun's eventual fate, but a reminder of its role in the larger narrative of the universe. There's also a more emotional resonance here. When we see R Doradus, a dim, nearly invisible dot in the southern sky, we are, in a sense, gazing at a cosmic elder sibling. It's further along the life path we too will follow. It stumbles through the slow-motion death of a star not with violence, but with graceful shedding, rhythmic pulsations, and a silent expansion. It is a gentle giant, laying itself bare before collapsing inward and fading. Eventually, R Doradus will cast off its outer envelope entirely, leaving behind a glowing shell of gas, what astronomers call a planetary nebula, surrounding a dense, hot white dwarf at the core. Our Sun is destined for this same end. It will not die in a supernova, as massive stars do, but will instead collapse into a white dwarf roughly the size of Earth, composed mostly of carbon and oxygen. It will glow faintly for billions of years, slowly cooling as it drifts through space, a relic of a once luminous past. This fate may seem tragic, but it is in fact beautifully necessary. Without the deaths of stars like R Doradus, the galaxy would be devoid of the elements needed to build Earth-like worlds. Every atom in your body heavier than hydrogen was forged in the heart of a star and released by the deaths of stars like this one. R Doradus, shedding its mass into the void, is seeding the future. Perhaps the atoms it expels today will one day become part of a new planet, orbiting a new star, circling a new hope. The parallel with the Sun also offers a sobering perspective on time. While it is comforting to think of the Sun as an eternal light, it is in fact a transient phase in a stellar life cycle. We are lucky to be alive during the brief moment when our star is stable and nurturing. Eventually it too will change, grow, and die, just as R Doradus is doing now. Earth, and all the life upon it, exists in a temporary window, nestled between the violent birth of the solar system and its inevitable transformation. From a scientific point of view, R Doradus is a natural laboratory, allowing astronomers to test theories about solar evolution, mass loss, convection, and dust production. The lessons we learn from this star directly inform our models of the Sun's future behavior. Instruments that track the flow of gas, the formation of molecules, and the expansion of the star's shell help us simulate what will happen to our own solar system. In this sense, R Doradus isn't just a distant object, it's a mirror, a time capsule, and a warning. The quietness with which this transformation occurs is perhaps the most profound aspect. Unlike supernovae, which explode with tremendous violence, the death of a sun-like star is more of a dissolution than a detonation. It is a long, drawn-out exhale, a release of light, warmth, and the elemental ash of its own nuclear fire. R Doradus reminds us that not all endings are abrupt. Some come slowly, with beauty, complexity, and enduring significance. And just as astronomers are watching R Doradus now, measuring every tremor in its shell, every twist in its dusty breath, future observers, perhaps not even human, may watch the Sun with the same tools, tracing its expansion, its reddening hue, its gentle, final glow. It may be difficult to fully internalize the idea that our bright, reliable Sun will one day look so different. But the physics is undeniable, and R Doradus stands as the living proof. It shows us that even the most familiar things, like sunlight, are temporary, transformative, and bound to a greater cycle. R Doradus is the sunset of a star. And from it, we see not only the close of one stellar chapter but a glimpse into the twilight of our own. Astronomers have always sought to understand the life cycles of stars, not just in broad strokes, but in exquisite, intimate detail. And among the many stars scattered across the southern sky, R Doradus has emerged as one of the most important and captivating targets of long-term study. Despite its relative obscurity in the public eye, scientists are watching it closely, and for good reason. This seemingly unassuming red giant serves as a cosmic laboratory for observing, testing, and refining our understanding of stellar evolution, particularly during its final and most complex stages. Why, among the billions of stars in the galaxy, does R Doradus command such attention? The answer lies in a powerful convergence of accessibility, relevance, and activity. R Doradus is not just a red giant, it is one of the closest and largest red giants to Earth, located at a mere 200 light-years away, practically next door in cosmic terms. This proximity grants astronomers an extraordinary opportunity, They can resolve its features with incredible precision, detect minute variations in brightness, track material being ejected into space, and even detect molecules in its atmosphere, details that would be impossible or uncertain with more distant red giants. The timing of its evolutionary phase is equally important. R Doradus is currently on the asymptotic giant branch, AGB, a fleeting, volatile chapter in a star's life that is notoriously difficult to model and observe due to its chaotic nature. It is in this phase that the star undergoes large-scale pulsations, sheds mass at an increasing rate, and prepares for its final transition into a planetary nebula and white dwarf. It's like catching a glacier just before it calves into the sea or a volcano moments before it erupts, a moment of change packed with clues about everything that came before and everything that follows. For astrophysicists, studying a star in the AGB phase provides crucial insights into stellar aging, particularly the processes that dictate how stars die, how they shed their outer envelopes, and how they enrich the cosmos in the process. The rate and nature of mass loss, for instance, remains one of the most significant uncertainties in stellar models. We know that low to intermediate mass stars like R Doradus and our Sun lose a substantial portion of their mass before ending their lives. But the mechanisms behind that loss, how it starts, how it escalates, and what shapes it, are still being worked out. R Doradus provides real-time data to address these questions. Its proximity means that individual layers and features of the star can be resolved with high precision using stellar interferometry, radio telescopes, and infrared observatories. By observing changes in its outer layers, measuring the movement of dust and gas, and analyzing its light curve over time, scientists are slowly piecing together how such a giant star breathes, how it ejects material, and what role pulsation, convection, and magnetic fields play in this process. Another reason why R Doradus is being so closely watched is its surface complexity. As previous interferometric observations have shown, its surface is far from smooth. Instead, it is shaped by colossal convective cells, temperature gradients, and possibly star spots, all of which contribute to irregular brightness patterns and asymmetric mass loss. This complexity, while a challenge for observational techniques, also provides an unparalleled opportunity to test the limits of stellar modeling. Any successful model of red giant behavior must now account for the chaotic surface dynamics that R Doradus exhibits. Perhaps one of the most groundbreaking areas of study surrounding R Doradus is in the field of stellar chemistry and molecular astronomy. Using instruments like ALMA, the Atacama Large Millimeter/Submillimeter Array, and the Herschel Space Observatory, astronomers have detected the presence of water vapor, silicon monoxide, CO, carbon monoxide, CO, and other molecules in the extended atmosphere of R Doradus. These molecules not only hint at complex chemical reactions taking place within and around the star, but also provide valuable tracers of mass loss, temperature gradients, and shock waves resulting from pulsation. The presence of such molecules in significant quantities is rare and intriguing. In cooler regions of the star's outer atmosphere, dust begins to condense and form grains. These grains, composed of silicates, carbon, and other compounds, interact with radiation pressure, effectively pushing material outward and helping drive the stellar wind. By mapping where these molecules form, and under what conditions, scientists are learning how dust grains form in stellar atmospheres, and by extension, how they go on to seed the interstellar medium with the raw ingredients for new stars and planets. The richness of the data collected from R Doradus is especially critical now, as the field of infrared and submillimeter astronomy experiences a golden age. New telescopes, such as the James Webb Space Telescope, JWST, have the sensitivity and resolution to observe dusty envelopes and cool outer atmospheres with unprecedented clarity. R Doradus is already being eyed as a prime calibration and science target for JWST. Its detailed observations could serve as a benchmark for understanding other red giants, both near and far. Moreover, the variability of R Doradus offers yet another dimension of insight. Its semi-regular pulsation, oscillating roughly every 332 days, acts as a cosmic heartbeat, a cyclical pattern of expansion and contraction that allows astronomers to study internal pressure waves, track material movements, and refine models of stellar interiors. These pulsations may also generate shock waves that propagate through the atmosphere, contributing to mass ejection events and dust formation. Each pulsation is a natural experiment, a test of how the star responds to internal and external pressures over time. Let's not overlook the potential companion hypothesis either. While no definitive companion has been found orbiting R Doradus, subtle hints, like asymmetric mass loss and non-uniform shell structures, suggest that it might not be alone. If a binary partner is discovered, R Doradus would become an even more vital testbed for understanding how binary interactions shape stellar evolution, especially in the AGB phase. Such systems are known to produce spiral dust patterns, accretion phenomena, and exotic outbursts, all of which are phenomena that connect the evolution of one star to another in profound ways. In addition to all these scientific reasons, R Doradus also fulfills a more abstract but equally powerful role in modern astronomy. It is a symbol of cosmic continuity. In a galaxy filled with extreme and often violent phenomena, gamma-ray bursts, quasars, supernovae, R Doradus tells a quieter, more patient story. It speaks to the gradual, inevitable process of change that even the most stable and familiar systems must eventually undergo. It is a meditation on time, on mortality, and on renewal. By watching R Doradus closely, scientists are not only decoding the fate of one star, but they are also laying the foundation for understanding how stellar populations age and die across the entire galaxy. The data obtained from this single red giant informs models used to predict the behavior of billions of similar stars, from our galactic neighbors to distant clusters and even galaxies beyond the local group. This means that every observation of R Doradus carries with it an outsized impact, a ripple that extends across cosmic time and space. The future of R Doradus research is bright. With ever more advanced instruments coming online, we will soon be able to monitor its surface in real time, track individual convective cells as they rise and fall, and create dynamic, 3D maps of its atmosphere. These developments may reveal surprises, perhaps undiscovered processes or unexpected behaviors that challenge existing theory. That's the beauty of watching a star so closely. You're never just seeing the present, you're anticipating discovery. In the end, the story of R Doradus isn't just about the science. It's about the universal story it tells. A story of transformation, of slow unraveling, and of the quiet dignity of endings. By learning from this giant, we come to better understand not just the cosmos, but the fate of our own star, our own world, and the very materials that make up our bodies and breath. R Doradus is a dying star, yes, but in that death is a fountain of knowledge, a beacon for astronomers, and a reminder that even the quietest processes can echo loudly across the universe. R Doradus, in all its slow, flickering glory, does more than just illustrate the end of a star's life. It teaches, not through explosive drama or violent collapse, but through steady persistence. This one star, swollen, cooling, and quietly unraveling, embodies the essential processes that allow galaxies to grow, evolve, and recycle themselves. R Doradus is a living lesson, and its value to astrophysics lies not only in its immediate characteristics but in the universal principles it helps us uncover. Stars are the fundamental engines of galactic evolution. Every major phase of a galaxy's life, its shape, color, chemical composition, and star-forming potential, is governed by the birth, aging, and death of stars within it. While massive stars get much of the attention for their short, energetic lives and spectacular deaths, it's the quieter, long-lived stars like R Doradus that do most of the heavy lifting when it comes to enriching the cosmos. They may not explode in supernovae, but their slow, consistent contributions to the interstellar medium make them no less vital. One of the most important lessons from R Doradus lies in its role as a chemical recycler. As it nears the end of its life, R Doradus is shedding its outer layers rich in elements forged by nuclear fusion. This is not just mass loss, it's mass redistribution. The carbon, nitrogen, and oxygen being expelled are not wasted. They reseed the interstellar medium, becoming the raw material for the next generation of stars and planetary systems. Without this process, galaxies would run out of the fuel needed to make new stars within a few billion years. When we trace back the origins of complex molecules found in gas clouds or on planetary surfaces, we often find their ancestry in stars like R Doradus. For example, the carbon in organic molecules, the oxygen in water, and even some of the metallic elements in rocky planets were likely expelled from red giants or asymptotic giant branch (AGB) stars. R Doradus reminds us that life's building blocks are not just formed in stars, but delivered by them, one pulsation, one dusty breath at a time. But R Doradus teaches more than just chemistry. It also offers insights into how galaxies maintain their dynamism. A galaxy is not a static structure, it's a constantly changing ecosystem of stars forming, living, dying, and enriching the medium in between. Red giants are key players in this ongoing transformation. Their mass loss doesn't just enrich space, it also shapes galactic structure. The dusty winds from stars like R Doradus help form the diffuse interstellar clouds seen in galactic disks. Over time, these clouds collapse under their own gravity, forming new stars. But even before that collapse, the dust and molecules from R Doradus alter the opacity of the interstellar medium, affecting how light travels through the galaxy and how energy is transferred between regions. This means that a single red giant's life can subtly influence the entire radiative environment of its surrounding neighborhood. In this sense, R Doradus is not just fading into obscurity. It is feeding the galactic ecosystem, supplying materials, shaping energy flows, and enabling the conditions necessary for stellar renewal. Its seemingly quiet existence contributes directly to the long-term viability of galactic evolution. Another profound lesson we gain from studying R Doradus is a deeper understanding of stellar population demographics. Galaxies, especially spiral ones like the Milky Way, contain billions of stars in various stages of life. To make sense of this complexity, astronomers develop stellar population synthesis models, which require accurate templates for different types of stars. R Doradus, with its well-characterized size, mass, variability, chemistry, and spectral properties, serves as a cornerstone data point for models that aim to simulate entire populations of AGB stars across various galaxy types. This is particularly important for understanding distant galaxies, where individual stars can't be resolved. In those cases, astronomers must infer galactic properties based on integrated light, the sum of emissions from all stars within a galaxy. If models of AGB stars are off, even slightly, it can dramatically affect the interpretation of a galaxy's age, metallicity, and star formation history. R Doradus provides a critical calibration point, one of the few nearby red giants whose physical parameters can be studied in great detail and used to refine these broader models. Moreover, as a variable star, R Doradus helps illuminate the internal physics of pulsating giants, an area rich with unanswered questions. Its semi-regular variability, combined with its enormous size and extended atmosphere, provides an ideal setting for studying nonlinear pulsation mechanics, shock wave propagation, and radiative hydrodynamics. These are complex phenomena that govern not only brightness changes but also dust production, molecule formation, and mass loss rates, all of which feed back into the galactic environment. The lessons extend to the study of dust formation itself. Unlike explosive supernovae, which generate a sudden shock of particles and radiation, red giants like R Doradus create dust slowly and steadily. This allows scientists to observe the gradual nucleation of dust grains, understand the role of molecule clustering, and trace how different elements condense under varying pressure and temperature conditions. It's a unique opportunity to study a process that's critical not just for astronomy, but for astrochemistry, planetary science, and the search for life beyond Earth. R Doradus also reminds us that stellar death is not a single event, but a process stretched across tens or hundreds of thousands of years. It challenges our human-centric perception of time. From our perspective, the star seems almost frozen in its final phase. But in stellar terms, it's in motion, breathing, losing mass, changing its surface, adjusting to internal imbalances, and preparing for the quiet brilliance of its planetary nebula phase. This perspective has broader implications for how we think about time in the universe. Stars like R Doradus provide temporal context for cosmic processes. Their long lifespans and drawn-out deaths allow us to better sequence galactic events, understand the pacing of star formation and death, and appreciate the recycling loop of matter that spans billions of years. Importantly, R Doradus also serves as a bridge between theoretical models and observational astronomy. Its relatively close distance makes it a prime test subject for theories of stellar convection, molecular chemistry, dust grain growth, and mass loss mechanisms. Observations from telescopes like ALMA, Herschel, Spitzer, and eventually JWST are constantly compared to simulations and predictions. When models fail to replicate what we observe in R Doradus, it signals a need for refinement, revision, or even radical rethinking. This interplay between observation and theory is the engine of scientific progress in astrophysics. R Doradus drives that engine forward by providing a rich, accessible case study. Every molecule detected, every pulsation measured, every asymmetry mapped. These are not just data points. They are pieces of a much larger puzzle about how stars evolve, how galaxies breathe, and how matter travels from one form to another. And of course, there is the deeply personal dimension. When we look at R Doradus, we are looking at the future of our own star. The sun will one day tread this path, expanding, reddening, shedding its layers, and becoming a beacon of dust and gas for the next cosmic chapter. In this sense, R Doradus is not just a teacher, but a harbinger, a glowing reminder that even the most familiar things are temporary, and that from the twilight of one star may come the dawn of countless others. This lesson is perhaps the most profound of all. R Doradus shows us that the universe is not a place of static permanence, but of endless transformation. Nothing is wasted. Matter is not destroyed but reconfigured. What fades from view is not lost, it is recycled into the luminous bodies of tomorrow. Galaxies are not built by explosions alone but by the quiet generosity of dying stars, giving of themselves so that the cycle may continue. So when scientists watch R Doradus so closely, when they devote years, even decades, to charting its changes, they do so not out of idle curiosity, but because within this one star lies 1,000 lessons about how the universe works, evolves, and renews itself. R Doradus is not simply a red giant. It is a living manuscript of stellar evolution, a thread in the fabric of galactic life, and a teacher of cosmic truth, waiting patiently for those who look closely enough to learn. It's easy to overlook R Doradus. For most, it's an unfamiliar name. A dim red smudge in the southern skies, far from the grandeur of Orion's belt or the captivating flare of Sirius. To the naked eye, under typical conditions, R Doradus is barely visible, quiet, unassuming, cloaked in the backdrop of more dazzling stars. And yet, this humble, overlooked star plays a disproportionately large role in the cosmic story. It stands as a profound example of how some of the most critical forces shaping the universe go unnoticed, silent but transformational. R Doradus is the kind of star that refuses to announce itself with flash or fury. It doesn't explode into a brilliant supernova. It doesn't launch violent jets or blaze across the sky with searing intensity. Instead, it shuffles toward its end, pulsing rhythmically, exhaling dust and gas into space, and changing everything around it in slow, imperceptible ways. And yet, through this soft, steady metamorphosis, R Doradus performs one of the most pivotal tasks in the universe: the quiet construction and redistribution of matter that will one day become planets, comets, asteroids, and life. To grasp the true impact of R Doradus, one must look past its appearance. You have to see with infrared eyes. In visible light, R Doradus is underwhelming. But switch to the infrared spectrum, and it becomes one of the brightest stars in the entire sky. In these wavelengths, it is a blazing furnace of activity. This is a reminder that reality often lies just outside of what we can naturally perceive. Our human senses are tuned to a narrow band of light, and R Doradus teaches us that the most significant truths can hide in the unseen. It also challenges our assumptions about importance and visibility. In popular culture, the stars that capture attention are the explosive ones, the supernovae, the neutron stars, the gamma-ray bursts. But these events are rare. R Doradus, and stars like it, are common and consistent, and they are doing the heavy, foundational work of cosmic evolution. They are the carpenters of the galaxy, building the interstellar medium atom by atom, molecule by molecule, dust grain by dust grain. And yet, because they don't dazzle the eye, they often go unappreciated by all but the most devoted observers. It is also a lesson in humility. From Earth, R Doradus looks like a faint whisper, a minor note in a sky full of louder tones. But scale betrays us. This faint point of light is a colossus, over 350 times the diameter of the Sun. If placed in our solar system, it would engulf not just Earth but Mars, and stretch halfway to Jupiter. It's a reminder that what we see isn't always what is. That the universe is filled with entities far larger and more consequential than they appear, obscured by distance, perspective, or the limitations of our senses. Its impact also lies in how R Doradus challenges and refines our understanding of the life cycle of stars. For centuries, humanity viewed the stars as eternal and unchanging. It wasn't until the last century that we began to understand that stars live, evolve, and die. And in observing R Doradus, astronomers are not simply watching a star, they are watching time in motion, the slow unraveling of stellar structure, the movement of elemental materials from one state to another. This process underpins the story of how galaxies grow, how solar systems form, and how the periodic table is written in the sky. And as humble as R Doradus appears, it is influencing cutting-edge research across disciplines. Astronomers studying star formation rely on understanding the mass loss from red giants like R Doradus. Astrobiologists trace the delivery of carbon and water, key ingredients of life, back to AGB stars such as this. Planetary scientists explore how dust grains expelled from giants accumulate into planetesimals. Even cosmologists, building models of galaxy evolution and large-scale structure, must account for the quiet, persistent contributions of stars like R Doradus to the chemical evolution of galaxies over billions of years. In this way, R Doradus is part of everything. Its atoms may end up in the clouds that birth stars, or in the ice that forms comets, or in the crusts of new planets. Long after it has faded from view, its envelope dispersed, its core a cooling white dwarf, the materials it released will continue to participate in the ongoing narrative of the cosmos. The carbon in a tree, the oxygen in your lungs, the iron in your blood, perhaps even a grain of dust that eventually becomes part of a spacecraft, or a human cell may have first formed in the extended atmosphere of R Doradus. That is no small role. That is not the work of a humble star, but the legacy of a cosmic architect. Its importance also stretches into the cultural and philosophical realms. R Doradus reminds us of the value of deep attention, the value of looking closely at things that are easily overlooked. It reminds us that not all phenomena reveal their significance immediately. Some require patience, time, and the willingness to look in the right spectrum, ask the right questions, and embrace complexity. In many ways, R Doradus reflects ourselves back at us. Humanity, too, is small in cosmic terms. Our planet is a pale blue dot around an ordinary star in an average arm of a spiral galaxy. But like R Doradus, we possess the potential to affect change far beyond what our visibility would suggest. Through our tools, our science, our curiosity, we can reach across the stars, detect the pulse of a distant red giant, and learn from its silent rhythms. Even the way we learn from R Doradus is a symbol of how modern science works. It is not the product of a single observation or telescope, but the result of decades of study, hundreds of researchers, and thousands of hours of observation across the electromagnetic spectrum. From infrared satellites to radio interferometers to space telescopes and computer simulations, R Doradus has become a touchstone, connecting fields as varied as plasma physics, stellar evolution, atmospheric chemistry, and cosmology. And despite all of this, it remains humble. Still faint. Still dim to the unaided eye. A brilliant paradox, a barely visible object that reshapes our understanding of the universe. It's easy to walk outside at night, look up, and feel overwhelmed by the brightness of stars. The night sky dazzles us with its complexity, but within that overwhelming canopy are hidden stories, slow, patient stories like that of R Doradus. Stars that aren't vying for our attention but are quietly, continuously making the cosmos what it is. It is a reminder to look deeper, to look beyond brightness, to appreciate the subtleties, the edges, the unseen. For often, it is in the quietest corners of the cosmos that the most essential stories are written. There is something hauntingly beautiful about a star that does not go out with a bang, but instead chooses to fade with grace. R Doradus is not a supernova waiting to happen. It will not light up the sky in a final, blazing death cry. There will be no shockwave to tear through the cosmos, no neutron star born in fury. Instead, R Doradus whispers its farewell. It breathes out slowly, rhythmically, its glowing envelope billowing into the void like the last sigh of an old giant. Its pulsations, gentle but persistent, ripple through its vast atmosphere. Every beat releases another veil of dust, another plume of gas, another chapter of the story it has carried for billions of years. There is no violence here. No drama. Only the long exhale of a star content in its purpose, aware of its role, and at peace with its transformation. In that gentleness, there is power. There is poetry. There is truth. R Doradus is a red giant, but also an artist. With every molecule it casts into the interstellar medium, it paints new possibilities onto the canvas of space. It is seeding future solar systems, sketching out the outlines of unborn worlds. Perhaps some of its carbon will someday find its way into the soil of an alien planet. Perhaps some of its dust will form the icy shell of a comet that sails past a new sun. Perhaps some of its oxygen will one day shimmer as part of an atmosphere blue and bright. And when it is gone, when its last outer layer has drifted away, when only the silent ember of a white dwarf remains, its influence will still echo. Not in brilliance, but in presence. In continuity. In the quiet fertility it left behind. Look at the night sky, and you may not see R Doradus. It hides behind the veil of the visible, too dim for our casual gaze. And yet, through the lens of infrared, through the calculations of astronomers, and through the dreams of those who listen closely, it emerges as a titan. A gentle titan. A teacher. A sculptor of the future. It reminds us that not all endings are sudden. Some are slow dissolves, luminous fade-outs that leave behind legacies rather than voids. We so often imagine stars as fierce and eternal, but R Doradus shows us their fragility, their temporariness, their willingness to give themselves up to the universe. And in that surrender, they become more than themselves. They become cycles. They become gifts. So let us remember this: a quiet star, barely visible, drifting 200 light-years from Earth, is helping write the story of what comes next. It asks for no audience. It seeks no praise. It simply lives. And slowly dies. And in dying creates. In the vast orchestra of the cosmos, R Doradus is not the drumbeat or the trumpet call. It is the long, lingering note on a cello, soft, resonant, and unforgettable. A note that continues even after it can no longer be heard. A note that becomes silence. And then, somehow, becomes everything. R Doradus is the universe at its most introspective, a cosmic elder reflecting in silence, leaving behind not wreckage, but potential. The gentle red giant. Fading. Breathing. Becoming. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.